see.
So, is Jason still?
He's on.
He's in G-Chat.
Oh, we can go.
I mean, so basically, this was the only contrast that I was getting
anything that looks reasonable.
Yeah. And there wasn't anything that looked. Oh. Okay, great. And this was the only one. Oh, sorry. And any conditions, or sorry, any analyses that were between groups were just showing up as like completely, almost. I mean, basically null results. And so I wanted to do some, so I'll kind of take you through what my thought process was.
Okay, yeah, go ahead.
Address these as we go. So this was the looking at the main effective condition. So this is the rhythm minus baseline minus normal minus baseline, supposed to be at least for both AWS and ANS. And so when I run that analysis, actually I already have some of these up. So, I guess I already ran it. So just plot it. So this was
Right, that is.
So this looks somewhat reasonable. There's greater activation in like posterior temporal areas, anterior insula, some SMA, potentially.
Could you try one thing just quickly,
yes.
Because just in case that happens to show pretty much the same results or similar. Yeah. In the contrast, instead of doing the 0.5.5, do 1 0.5.5. Yeah, I'm just run it again. In here, you're interested at just the average across all subjects, right? So basically, across both groups, look at the average of the difference between the normal versus rhythm conditions.
Yes.
Okay.
So that produces the same.
Okay, that's fine. This is perfectly valid. I'll go into the details later if you want to explain.
So then after doing that, I thought, okay, well, I want to see what the effect looks like for just the people who stutter and just for the controls.
Mm-hmm.
So then I created a second, so for just the controls, this was the second level design file that I created.
Right. And I didn't ask the question, but the motion centered is basically the, what measure is it?
Let me just show you what the participants.tsv file. Motion centered is the average motion in each subject, so listed as a vector across all the subjects, and then centered so that the mean of all of them is 0.
Okay, and this is across all subjects, including both groups, not centered separately or anything like that, right?
Correct.
Cool. Okay, no problem.
So when I do this with the 001, and I was running it, and
yeah.
I'm guessing you already know that it's not going to come out right, but
no, this is actually fine. That should actually come out as the average in the. Yeah, I think this should look fine.
Okay, so then I'll run that, and then I basically get this weird result that doesn't look anything like the. And so I could like lower the threshold, and I mean it's just at a very, very high threshold, I guess.
Yeah, but how many subjects do you have in that group, basically?
16 or 17.
Right. So there's, I mean, that might be just because of the low number of subjects in
Sure.
a single group, right?
Now let me show you.
But still, yeah. Yeah. And did you look at the other group as well?
Yes, I did, as a matter of fact. So, so the other one, the configuration file looks like this. So basically the same, but the group is changed.
Mhm.
And when I run that one, I'm like, oh, it's still null effect. But if I switch this to two-sided, I notice that there's the same spot. So when I change the threshold, it's actually the exact same as the other one, but in order.
Okay, so let me think about it for a second then. Right. So you're not just that. Okay. So when you're actually looking at the group difference, yeah, sorry about that. So, okay. So forget that when I said it was fine, it was, sorry, it was not fine. If you want to look at the average of the group within the AWS using this kind of like valid column, that basically adds that redundancy, you still need to use the 101, let me check. Yes, 101 for looking at the within that group. Otherwise, you're looking at just the difference, because what is happening is that the valid column is getting the value of the average of the other groups that is not modeled. The column in the AWS, which has zeros for the other group and ones for this group, is going to capture the difference between the two groups. So that between the valid and the AWS, you are capturing both effects, but in a weird way, because one is capturing, valid is capturing one, and AWS is capturing the difference between the other and the one. So that's why you need this 101 contrast to look at the average value within the group, within the AWS group.
So I kind of thought about that a little bit and then tested out doing the same thing with the 101.
Right. I mean, if all of this is confusing, which I imagine it is, one way to go about it is to just basically add the nonce to the group definition. So basically, instead of just using the valid, just add the nonce to the AWS and the what was the other PWS groups, so that you can forget about including valid. You don't need to include them. Just include that.
So
and that will work.
Switching that and getting rid of the valid column.
Right. Well, still keep the valid column for other analysis where you will want to pull all of the both groups together, but that also works.
Okay. So because when I did run this one.
Yeah. In any way, exactly that in the way that it was defined should work just fine. Now that should show you the average group within the AWS, the average effect within the AWS, and the effect here is basically the normal minus the RIF condition.
And this looks much more like the
like both groups together. Yeah, that makes sense. Yeah.
So that made me wonder whether the group effects. So let me just look at the main effect of group. So the main effect of group across the speech minus baseline condition was specified like this. Yeah. Does that?
That's, let me see, valid motion, the difference between the two groups, that's perfectly fine, right? And that's for the speech minus baseline, right?
Yes.
Right, yeah.
Okay.
Yeah, that should work fine as well. That should be the same as what you were getting before with a valid motion and just one group and doing the 001 contrast.
Okay. Oh, okay. Wait, this should be the same as, sorry, say that one more time.
So remember when you had another design that was valid, motion center, and AWS, and you were using a 001 contrast, and we thought initially that was looking at the average of the group, and now it was actually looking at the difference between the two groups. That difference in the two groups is basically the same as what you should be getting, exactly the same as what you are looking in this analysis.
Okay, but the valid doesn't need to be specified as a 1 in this case?
No, because, well, it would, I mean, conceptually, it would be like a 101 minus 1001, and the ones kind of cancel out. So you have a vector that says 1010 that is looking at the average within one group, another vector that says 1001 that looks at the average between the two groups, and you want to subtract those vectors to get the difference between the two groups, so you get 00 plus 1 minus 1.
Gotcha. Okay. Yeah, so when I put that one, oops, sorry. I run it under a different.
Okay.
So let's.
All right, but also this is looking at a speech minus baseline, right? The other one you were looking at the rhythm minus.
Correct.
Right.
Yep. So let me rerun this. I think I may have run it at it where it was different.
Yeah, and then there is also one subtlety here, which is that you are controlling for motion, basically. So you are trying to discount any potential difference between the two groups that could be accounted for by just motion difference between the two groups. So if there are any difference between the amount of motion between the groups, you're trying to correct for those, basically.
Are there any differences? There's only there's slight differences, not large ones.
Between correcting and not correcting for motion, you mean?
Between no, I mean between the average motion in subjects in the
I don't know in this data set are there. So basically, you could look at those numbers. Basically, the numbers that you enter into that column and look at whether they show any difference between the two groups, right? But I don't know a priori.
Right, and they don't appear to.
They don't appear to have. Okay,
yeah,
cool.
Exactly. So yeah, I was wondering if that extra one was. So if we did add that one in there, that would be a valid.
Right. In the
group.
Could you repeat the question? Sorry, I'm not sure.
So if I change this to a 1, that would do something that.
That's a complicated thing. Let me see if it has a misinterpretation. No, it doesn't have a misinterpretation. So the thing is that so when you have this design, basically you have 4 columns in the design matrix, and you're going to have 4 beta values, right? For the coefficient, the regressor coefficients. The thing is that because the columns are redundant, the first column and the third and the fourth are not linearly independent, because the third and the fourth column adds up to the first column. Then the beta values are not uniquely defined. So basically, if there is some effect that you want to capture that represents kind of like the average activation within one group, that is going to divide it into 2 portions, one that goes into the valid regressor and another that goes into the AWS regressor, the third column. And the same thing happens for the average effect in the other group. That is going to, some portion of that is going to go into the valid regressor, and the other portion is going to go to the AWS. And which portion go to which is totally arbitrary. You're going to get exactly the same fits where you put like 10% into the valid and 90% into the individual groups, or 90% into the valid in the first beta value and 10% in the other one. So there is no unique definition. The thing get actually assigned a value because the model uses this pseudo inverse, which is going to give you just the minimal norm. So it's going to give you among all possible solutions of combinations of beta values that produce exactly the same fit, is going to choose the one that has minimal norm. But that minimal norm is totally meaningless in terms of the interpretation of what is happening here. So basically, when it's basically like a non-uniquely defined effect, and when you try to look at something like that, you are combining something that is a portion that is not uniquely defined with a portion that you took care and has a misinterpretation, which is the difference between the 2 groups. And depending on how that pseudo inverse worked and which proportion of the average activation between the 2 groups put into the valid column, you are going to get a different number here. And so that's why it's not appropriate.
So, but does including it in the model also remove? So it's estimating that valid effect and the individual group effects separately. It's just not including that in what you're getting out of the contrast.
Right, exactly. When you do that, it's still doing the same thing. So so some portion of the effect is going to go into the valid column, and some portion of the individual group effect is going to go into the AWS column. But let me see if I can.
So
sorry, go ahead.
So if I just test it, if I got rid of that valid column and just use this new definition where I put should that work?
Yep, that works perfectly fine.
So let me try that. I get rid of, oops.
Exactly. So get rid of the valid, and you already have not numbers in the corresponding groups, right? At least in one of the variables.
The ones that are not being used, there's an NA.
Okay, cool. Okay, so that should give you exactly the same as what you were getting before, basically. But now the columns are not uniquely defined, so everything is a little easier to interpret, basically.
Yeah. So let's see.
Sorry, did I say the columns are not uniquely defined? I meant the opposite. The regressors are now uniquely defined, so yes. Everything makes sense. Sorry.
Do that. Okay, so that should be the same.
Yeah.
Okay. Well, I was hoping that this discrepancy would have led to some sort of
Different result.
yeah. Now there's literally no differences. Okay.
Yeah, I would try really with a little bit of a less conservative high threshold because you don't have that many subjects, so it's very difficult to reach that level of significance just with that relatively few subjects within each group for a between group difference. So you're looking at the interaction of a within subject effects, which is the and a between subject effect, and you don't have that many subjects per group, so it's difficult to reach this 0.001 at the voxel level, which means that.
Well, this is not an interaction necessarily. I mean,
This is actually looking at the average speech minus baseline effect, okay, so I'm still looking at that. Yeah, right.
And this is something that lots of previous studies have found results for, which is why it's surprising.
And how do you look at the individual groups and the results to see what you learn from that?
So I tried a couple of other things. Go back to so I also tried.
And have you tried not removing the motion correction if you didn't find any amount of motion, just to make sure that this is not some strange effect of that? Basically.
I can try that.
Yeah.
Try that right now.
Yeah, exactly, something like that.
Same thing, basically.
Pretty much the same. Yeah. So there was no difference between the groups, then the motion shouldn't have corrected for that, and probably the motion doesn't seem to actually account for much activation difference between subjects. Otherwise, you would have seen like a difference in sensitivity here, basically. So yeah, okay, so that's fine.
So then so let me show you something else that I did. So then I thought, okay, what does speech minus baseline look like for each of the groups separately? So when I did that, I specified this. Maybe this valid doesn't need to be there. But
yeah, depending on whether you put the nonce on both. Oh, well, the nonce. No, yeah, that.
The nonce are both.
Oh, wait, there is a subtlety here, right? No, you were looking at the difference between the two groups across both groups. This is fine. Yeah. No.
So should I get rid of the valid here, or does it matter?
I think it doesn't matter. You can get rid of the valid, but you still need to put either the other group or basically create a motion center covariate that only applies to that group to make sure that you're only entering the analysis for that group otherwise. Or just keep the valid and do exactly what you're doing there, and that is still modeling. It's going to give you pretty much the same. Yeah.
Okay. So let me just run this. So here's just the control group speech minus baseline.
Mm-hmm.
Looks relatively normal.
Yep.
And you can look at both sides. Now when I run the stuttering group speech minus baseline, do the same thing, just replace
exactly, yeah.
There. Just run that again, just on the safe side. And get a very similar plot. No, oops.
Could you put them side by side just to quickly look at any? I mean, we shouldn't over interpret the difference, but just to see those differences.
Right. Yep. Right. Oh, this is the one. So this is. So slight differences, but again, you're right, hard to interpret.
Yeah, no, that's fine.
So okay.
Relatively similar.
But
I mean, I was looking at whether there was any difference in, like, if for example, the PWS group is less homogeneous, then you would see like a decrease in power, basically. So everything will be similar but less significant in one group compared to the other, as opposed to being actual difference in the amount of activation, which would be like a more heterogeneous type of pattern difference between the two groups. But in here, I don't see.
Right. There's a couple areas like anterior insula that are, you know.
Well, the color map of these two plots is not necessarily the same, right? So we cannot tell for sure whether those. Yeah.
So then, just to see what would happen, I did a comparison of the two groups, but then I put a 1 where the valid was. I included valid and put it as a 1.
Right, but that is going to be like a mixture of the average activation effect between and the difference between the groups. So it's going to, depending on what percentage went into the valid and what percentage of the activation went into the individual columns, you're going to get a different plot. So that is not something that would be particularly interpretable as a.
So if we just take a look at it, just to
sure. No problem.
If we do this, we get this contrast that when you look at the peaks of this contrast, it lines up pretty well with the differences between these contrasts.
Mm-hmm.
So, for example, this spot is visible in the stuttering group,
right,
but not in the control group. Which So I thought to myself, does this represent the difference between the groups or not? And maybe you can give some thoughts about that.
Okay, so no, I mean, this represents an average of two things. So a weighted average of the difference between the two groups and the average activation between the two groups. And the weights in the way that you're averaging is totally arbitrary. How much weight it went into the average of the two groups and how much weight went into the difference between the two groups is totally arbitrary. It just depended on the way the pseudo inverse found that the minimal norm solution was for every individual voxel. So basically, you are doing like a weighted average of those two things using weights that are different for every voxel and totally arbitrary in a way, or at least almost impossible to interpret. Well, perhaps there is a way to interpret them, but there's no easy to do so. And because you're doing that weighted average, if you are looking at the difference and the difference goes into the same direction as the average activation in the two groups, then you're going to see like something that gets pumped up in the effect. And if the average activation goes in the opposite direction as the difference between the two groups, then the effect is going to be kind of squashed down. And all of this depends on which weights were actually used for that weighted average. So I wouldn't. I mean, this is just like a thought experiment, but I wouldn't put any like a type of practice for understanding how these things represent, but it doesn't really represent anything meaningful in terms of what your research questions, basically.
Okay. I just thought it looked interesting.
Right. Right, but it's basically just doing that average. And the problem is that it's not truly an average. Well, even if it was an average, it still would be very difficult to interpret, because why would you average kind of like the average activation with the difference between the groups? You are kind of like artificially inflating the things that go into the same direction as the average. So basically, if the average activation is positive, then you're going to be inflating the difference that go in between the two groups that go in that same direction. But if you had done changing the signs of the difference, for example, instead of doing like a 1 - 1 1, you use 1 1 - 1, you would get the opposite direction and the things that were actually larger in the other group were the things that would get weighted up. So again, it's not something that is any way to interpret them correctly. Sorry. I know that it looks nice because basically.
Oh yeah. No.
It's just not not anything that is easy to interpret or
Okay. Well, that's good to know at least. But okay, cool. I thought I would investigate it a bit, see if you thought. Yeah, that.
So that sorry, let me see if I can. Yeah, let me see if I can explain it. Let me share my window for a second. I mean, this is interesting to kind of like try to understand. It will be in line with what I was in any way thinking of talking about today. So let me see if I can share my window for a second and show something here. Let me see. Share. Oops. Oh, can you stop sharing yours for a second? And thanks. Let me see that. Okay, let me see if I have something here that I can. So let me do that. Let's say y equals 121 and now 1. Okay, so now I have something like that. Well, that was awful. Why didn't? Oh, because I should have used larger numbers. Okay, something like that. Okay, so imagine that this is your data, right? And you have these two groups. The first 10 subjects are one group, and the second 10 subjects are the other groups, right? And now, so this is my actual data, right? And now I have a design matrix I'm going to create that has basically that column. First, a column of all ones, then a column that goes. Oops. Well, I'm going to do that. That basically, so something like that, right? So this is my this is my design matrix. It has a column of all ones, then it has ones for this group and the other one for the other group. And now I do a regression of that. So I basically do beta. My beta images are these. Now I get these values. Well, okay. So how do you interpret these three things? So let me show first the actual data. Okay, so basically the way how these numbers relate to the height of these things. You would expect something to be 2 and something to be 1, right? And if I actually had created my design matrix like this, basically now my design matrix is something like that, and I do that regression. I will get two values, and the first value represents kind of like the average in this group, the ones, and the second represents the average in the second group. But that's not what I got. What I got was this. Let's see what these numbers mean. Basically, the 2, -1, and 0. And the only thing that they actually mean is that basically this level is represented by the sum of this number plus this number. So basically, if I do the 1-1 contrast, I'm looking at if I use let me do that basically. Let me just multiply 1-1 contrast times beta. That is going to be the average within the first group. It's basically 1. And if I do that, I'm going to be looking at the average between the second group, which is 2, basically. But the actual numbers themselves, they are totally arbitrary. I could have gotten here, instead of a 0, a 1. So for example, let's say that I instead of a 2, I could get like a 3 here. And then I just subtract 1 from everything. I do -1, I get -2 here, and I get -1 here. And they will basically add up in the same way. I will still fit my data as so basically my data gets fit by this. Basically, this is how I fit my data. And even though the individual, these values are totally arbitrary, the fit is exactly the same as I was getting when I was using only 2 columns, only that the actual numbers that are represented, they let me do that trick. And for example, just add up 1 to this, subtract 1 to the second one, and subtract 1 to the third one. And I would recompute, sorry, oops. I'm going to recompute my ifit2, and I should get pretty much the same thing now. Oops, I should have do the whole DOM, sorry. But basically, see now I changed my betas. I added one to this, and I subtracted 1 from this, and I'm getting exactly the same fit as I was getting before, right? So I plot my original data. And then I do the fit with that modifier, it's the same. And if I, instead of adding 1, I add 2, or I add 3, or I add any absolutely number, basically I would get exactly the same fit. And all of those will be exactly fitting the data in the same way. So how the pseudo-inverse kind of like gave me that combination, that particular combination, it did it because among all of the possible combinations, all of these that I was trying, that gave exactly the same fit, this is the one that actually has minimal norm, basically. Or at least it would be if I have done, that's probably not the one, but if I had done that, it would have been. This is the one actually that has minimal norm. The one that the way that MATLAB does this matrix inversion when it's rank deficient in this case is even more difficult to interpret than the one that I'm saying. But when you use a pseudo inverse, which is basically what SPM is actually eventually doing in here, this particular vector is again exactly the same thing. Yeah, I could do an ifit3 now with this particular vector, and if I plot that, sorry, I would still be fitting exactly the same data, basically exactly producing exactly the same fit as I was doing before. It's only that this particular combination is the one that produces a B vector of minimal norm among all the possible ones. The norm of B in this solution is the minimum among all of the possible Bs that will produce actually the same fit. But still, the combination, the things that you care about, the ones that which is the average within this group and the average within the other one, those numbers basically are still accessible. You only need to use those particular contrasts. So basically, for that, this new beta, which is using the pseudo inverse, that should still be 2 basically, and this should still be 1, which is basically the average within the one group and the other. And if you look at the difference between the two, you just have to do 1 minus 1 and still get the difference between the two groups, right?
Gotcha.
Even. So makes sense. This this is basically what it's because of this redundancy that you have non-unique which that non-unique coefficients, and that's what makes the contrast definitions a little bit tricky. That's why you need to add that one basically to get the average effect, because you know that the sum of those, that is uniquely defined because that's defined from the data. But which portion goes to the first regressor and which portion goes to the third, the sum is fixed, but the actual distribution is not fixed. It's totally determined by the way that the pseudo inverse is computed.
Gotcha. Okay, that makes sense.
And again, if you look at that thing, perhaps that you were looking at, that will be totally different depending on how you compute the beta. So if I do this, basically, now I use that contrast, it will be totally a different number, basically. For every way, you saw how before, for all of the different beta ways of computing the beta, the difference between the groups and the average group, those contrasts were meaningful because they were representing something about the data. They represented either the difference between the groups or the average activation within one group. But this particular contrast is not meaningful with respect of the data, so that is going to depend on which particular method was used to compute the betas, actually. And that's why I'm saying that is not particularly interpretable, because because of that, it all depends on how the betas were computed in this kind of like which portion of it went into the first into the value regressor and which portion went into the group regressors. Makes sense? Kind of like roughly.
In this case, that would just be like that 3 would be like the effect size of difference from 0, or from like the.
Right. I mean, it's tricky. It's this thing plus this thing, but plus this thing. But this thing is a portion that is totally arbitrary. How much it went into the value regressor? It's kind of like some portion of the average effect across the two groups, but which portion? How much of that depends on how the pseudo inverse applied the operation.
Okay.
Okay.
Cool.
Okay, sorry.
Okay.
Sorry that it was a very long explanation. I hope it made a little sense.
Yeah, no, that made sense. Okay, cool.
Okay, so any other questions about your that particular analysis, those that you were running?
Not for that one specifically. I had another question regarding doing a connectivity analysis. So we discussed in lab meeting potentially doing like a GPBI connectivity, and I was trying to figure out how to import the data from that have already been pre-processed for this pipeline into Khan, so that they could be denoised and then.
Oh, right. Yeah, it's pretty much straightforward. I mean, our pipeline basically is creating a COM project per subject, basically, for every it's kind of like under the hood, but it's basically doing that. So
Yeah.
one relatively straightforward would be to merge the projects that you care about at the group level. So if you would just merge the projects that correspond to the individual subjects and create a new project for that combination, that will have all of those preprocessed data already, basically.
So I tried to do that, but it seemed to, it thought that there were more subjects than there were.
So basically, it goes like this. You can go to project. Let me see if I recall how merge. Let me see. You go to the control box and click on merge, and it will ask you whether you want to add to the current project or create a new project. Say create a new project, so it's different. And then you say how many projects you want to merge, and that's going to be as many subjects as you have. So basically 31 or something like that. And then select the files. Basically, look at the con_something math files that our pipeline has created for every individual subject. When you do that, it will ask you to give a name to this new project and a location in your directory, and it will create a project that basically doesn't do anything with the data. It will just that project basically points to all of the data for every individual subject, and then you can continue denoising it and doing whatever you want with it.
Okay. Yeah, I think I forgot to put in. I left the 1 in that number of projects, and then
right. So it was just trying to do a single subject type of thing, right?
Yeah, something like that.
Anyway, I mean, give it a try and let me know if you run into any issues, because I haven't tried it myself with our particular pipeline, but I mean, conceptually it should work.
Okay. Cool. That's
okay.
all I have.
Sharing this. Okay. What would you like to do? I was thinking of kind of going over the examples of second level analysis. I have like a long list of potential second level analysis examples that we could go over, like how do you specify the contrast for the complex designs and things like that, what it means kind of like in terms of interpretation. But I don't know, do you want to do that, or do you have any particular questions that you would prefer me to go over, or particular things with your data sets? What do you think?
I think that would be great. I think what I was going to suggest is that given how Sol has this organized, that maybe we go through Matt's configuration files to make sure we're interpreting them correctly, but maybe it would make more sense to just take a step back and go through some examples just so we get a better understanding. Matt, do you have a preference there?
No.
All right. Well, okay, so I guess I'd vote for Alfonso just going through some examples.
Okay, so I'll let me see if I can share my window again. Then let's see. Let me see what I have. This. So I was thinking of just going through a few examples of experimental design that you could use. I present a few of these examples in the context of the Con workshop. So some of these are going to be just talking about connectivity values, but I mean, practice is basically the same. Whether you're looking at activation or you're looking at connectivity, basically you're looking at a map of voxels, basically, and you are asking a question about whether those maps are different between conditions or across subjects. So let me see. Do you recall vaguely, so before I start, do you recall vaguely the talk about the GLM analysis where I was talking about the 4 things that you need to specify for specifying a second level analysis, which go kind of hand to hand with what the things that we specify in our configuration files. This was basically, you have to specify which columns, basically, what effects go into your design matrix. This X is the design matrix, Y is the data, right? So the design matrix, what subject effects are modeled in your data. Then the second thing that you specify is a contrast across those subject effects, right? So if you enter 3 columns, 3 effects into your design matrix, you have to specify a contrast across those effects. And the third thing that you specify is which columns go into your actual data. And that is what I was calling originally conditions, but these are basically your different contrast that you are entering, and this is kind of like a repeated measures type of design. You have subjects, and you can have just a single column if you have just one data image basically per subject when you're looking at something like I don't know, speech activation minus baseline, and that is already a single image for a subject. You just enter that. But sometimes you want to enter repeated measures and enter multiple measures per subject. So you could potentially have multiple columns, and you just have to specify, well, what is each column? Which data are you putting in each column of your data matrix? So you basically specify them as different contrasts that you created during the first level analysis, and each of them is going to go into a different column of your data. So that's the third thing that you specify, which are the columns of your data. So basically which conditions or contrasts you're entering there, and then you enter again a contrast across those things. So basically this is the within subjects contrast. When you specify 4 different conditions or speech conditions that you care about, you have to specify what type of contrast you care about across those 4 conditions. And with those 4 things, you are fully defining your second level analysis. Does this all sound familiar, or do you want me to go into a little bit more detail about all of this?
Sounds pretty familiar to me.
Yeah. Same.
Okay. So then basically all of these examples, what I'm going to be talking is about those 4 things. Basically, I'm going to say for every example which subject effects do you need to model, which contrast do you use across subjects, which conditions or contrast you enter for the data, and which contrast you specify within subjects. And with that, we are going to go over a few.
Alfonso?
Sorry, go ahead.
Before we go forward, just a quick question about the previous slide.
Mm-hmm.
So in there, the design matrix doesn't include a column of 1s.
Right.
Is that?
That's perfectly fine. I mean, we're going to see a lot of examples. Some of them include a column of 1s, and some of them don't. And I'll try to explain why that is necessary. And if we had a column of 1 in this particular example, it would be just fine as long as we enter a 0, because the difference between the 2 contrasts is going to create a redundancy, the same thing that we were talking about before between the first column and these 2 columns. But since the contrast that we care about is the difference between the 2, that redundancy is going to go away when looking at the difference. So we care about that. But yeah, let me see. The rule of thumb in general for the design matrix are actually, well, I don't know if our scripts, the GUI, the COM GUI checks it, but I don't think our FL scripts check it. But I could actually make it so that it does the check, because it's a good way to detect when your design is invalid, basically, or you have done something weird, which is that typically are you familiar with the ideas of column space of a matrix and row space of a matrix? That's
Sort of.
well, let me put it in a different way then. So basically, you should, for any design matrix that you create, you should be able to create a linear combination of the columns of your X matrix that add up to basically 1s, all 1s. If that doesn't happen, if there is no way to create a linear combination of your columns that add up to 1, then typically you have an issue with your design, because that it has to be a very weird design for that not to be the case. So if for example in here you have a design like this, but this has a 2 in there, basically instead of having all 1s and 0s and all 1s and 0s, that has a 2 in all 1s, and the one subject has a 2, then basically you are not going to be able to create a linear combination that adds to all 1s, and that is a very good way to detect that something is wrong, like in this case. In this particular case, when you have 1s and 0s here and 0s and 1s here, adding these 2 columns is going to add up to a column of all 1s. So in the designs where you have actually an all subjects column, that already column is already adding up to all 1s. So that is always kind of like valid. But if you have a design that doesn't have that all subject columns, a good quick check is to check whether across the columns that you do have in your design, is there a way to create a linear combination of those columns that add up to that 1s? And if they do, then you're probably fine. Okay, makes sense. Okay, so I think I can skip this for another day, basically, which is kind of like the specifics of how you do. We can talk about this on another day. When you get this type of result, we will talk about this the other day, right? How do you specify the contrast, and what is the high threshold and the cluster threshold, and why do they exist as different things, and all of that. So I can skip that. I can go directly to the science. Okay, so let's start with the kind of like simplest effect possible. So let's say that you have, whenever I say connectivity, if I remember, I'm gonna switch that to activation. But if I don't, and I say connectivity, just in your minds, just switch that to activation, speech minus baseline, or whatever you think it makes more sense for our studies. But basically, one thing that you might want to look at is basically the simplest thing is to look at the average activation across the entire subject group. And how do you do that? Basically, you specify these 4 things. You specify a column. Remember that I said that you have to specify 4 things. Basically, this is the things that you enter into your design metrics, what is the contrast across those things, the things that define your actual data, which conditions go there, and then the contrast across those conditions. In the case where you just want to look at the average activation across all subjects, it's kind of like the simplest case. You just need to enter a single subject effects, which is the all subject effects, so basically a column of all ones, and enter a contrast of 1. And then if you have a single condition, let's say speech minus baseline, you just specify that single condition and enter a contrast of 1. And what that is happening is basically looking at creating a design matrix that has just a single column of all ones. The regressor coefficient for that value is going to represent the average activation within the group. So basically imagine that these dots represent the activation for your subjects, and I'm plotting here a covariate like H, but in this case we don't care about H because we are just looking at the average activation. So you have this cloud of points that are your different subjects, and the y-axis represents the actual activation of each subject. So what does this test do? This basically just looks at the average activation, basically the average of all of these dots, and computes an error bar around that and determines whether that average is above 0 or not. So basically you're looking at the average activation and determining whether, like using a statistical threshold, whether that average is positive or negative. And since we are looking at just, I'll talk later about how to do contrast across conditions, but in this case, we're going to be looking at just a speech minus baseline type of activation. So basically a positive number will mean that you have positive activation, a negative number will be negative, and a 0 activation, which is kind of like the null hypothesis in this case, will mean that there is no difference in activation between the speech and your baseline condition. And that's what you are testing, this hypothesis testing framework that we are doing to give us p-values and to give us clusters is effectively testing whether that thing that you are measuring, in this case, the average speech minus baseline activation, is actually different from 0 or not. That's the single thing. Okay, so this is kind of like the simplest possible scenario. You have just one group of subjects and you have one single condition, and you have to specify those things, a column of all ones and your condition and a contrast of ones. So now let's do the same thing, but now you have the age covariate. Since we use this example here where we have like the x-axis represent the age of the subject. What if we want to look at that type of regression? We want to create a regression line in here that fits activation versus age. So we are asking the question whether activation increases with age or perhaps it decreases with age. We want to test whether that happens. Basically, is activation correlated with age? How? And that is model. Basically, you create a column of all ones and you specify two factors now, two between subject factors. Instead of just specifying a constant term, which is what we were doing before, that was going to model just the average activation across all subjects, you specify one, the all subjects, and your covariate, the age covariate. And what that is going to happen is basically that if you think of the design matrix, you're going to get two regressors out of those, right? And then the all subjects regressor is going to represent the actual intersect of this line against it's called the 0 intersect. So basically it's how this line intersects with that y-axis here. The height of that intersect is going to go into the regressor of the all subjects, and the age regressor is going to represent the slope of this line. So basically it's a slope in units of activation per year. For example, if we are entering age by year, so basically it's the units of your activation divided by the units of your covariate. So basically if you get a 1, basically it means that for every year of age you get an increase in 1 units in activation in the speech minus baseline contrast. And that's what the regressor associated with the second column is going to get. And it's going to be positive if the correlation is positive, and that number is going to be negative if the correlation is negative. So when you think of what type of contrast do you care about for looking at whether those things, activation and age, are correlated or not, the contrast for that would be just specifying 0, 1, because what you're saying is that you just care about the slope of the regressor. You just want to know whether that is positive or not. So this contrast, and then again, you just specify the single condition and a contrast one across condition. This is going to looking at a correlation between activation and one covariate. And the way to specify it by using this 0, 1 contrast. And the reason why this is the case is because you know that the second the regressor associated with this second column of your design matrix is going to represent the slope of your numbers. The effects are going to be basically this type of activation divided by units of your covariate measure, and the significance is going to determine whether the slope is positive or negative, basically whether there is any association between those two things. So if you get a significant thing, basically you know that there is a significant association between your covariate and activation. Does it make sense so far? Okay, and the thing that I kind of like jump a little quickly about that, and we are going to talk about that in more detail now, is this y-intersect type of thing. So the all subjects, the regressor that is going to be associated with the first column is going to be the actual intersect of that line at the zero level of your covariate. And this kind of like applies in very general scenarios. When you have covariates and you are measuring anything else that is not the covariate, basically, it's going to be always interpretable as whatever thing that you are trying to measure by this effect at the zero level of that covariate that you are also controlling for. So that's why in this particular design, the all subjects, if I use a contrast of 1, 0, for example, what I would be actually testing is just what is the actual height of what is the actual average activation level for subjects that have 0 years of age. That would be a weird question to ask, but that would be actually the question that we'll be asking here, because the first column is going to contain that height, basically. And if we are asking whether that height is positive or negative, we are asking whether the average activation of 0-year-old subjects is positive or negative. So that is, if we ever want to ask that question, we would ask it using a 1-0 contrast. But because the 0 level of the age covariate is something that we can play with, we can actually center that covariate. We can actually ask different questions. Instead of, if we don't care about the average activation at 0 years of age, but we do care about what happens at 20 years, because that is, I don't know, in any way representative of our model. So we want to know what is the average activation in 20-year-olds, and we have this data, and we know that the activation is going to be correlated with age. How do we actually answer that question? How do we know what is the average activation of subjects of 20 years old? So the way to do that is basically exactly the same as we were doing here, but instead of, we basically want, I mean, conceptually, we want to move the y-axis to that 20-year-old level, right? Because in that way, the first covariate is going to be modeling the y-intersect, which is going to be at the proper age. So the way to move the entire cloud of points so that the 0 level of that in the x-axis is at the 20-year-old is by centering that covariate. So instead of using age as in the number of years of every subject, we subtract 20, well, I'm using the example of 25 here, so I'm going to say 25 from time instead of 20 from them, just not to confuse you. So I'm going to subtract 25 from every age, and I'm going to enter those as my second level, as my new age covariate. And then I'm going to use a contrast 1, 0, because now this contrast of 1, 0 is looking at the y-intercept, and the y-intercept, now the x-axis was kind of like shifted so that the y-intercept is at 25 years, at the age of 25. Now I'm asking the question of what is the average activation at that particular age. So this is a way to basically, this type of contrast and centering that covariate is a way to basically ask the question about something else. So typically, I'm going to show you a few more examples of this in things that are a little bit more relevant. But this is a little bit of an introduction to get the idea, the general idea that by centering, you center a covariate when you want to look at some other effect at some particular level of that covariate that you care about. Because the other effects are always going to be at the 0 level of your covariate. You can change what that 0 level of the covariate is so that you are effectively looking at whatever arbitrary levels you care about that covariate. Does this make sense? Okay. And this particular contrast, in particular, if you want to look at the activation of the subjects in 25 years, you just enter that same model as before, but now you enter the covariate centered and then enter that contrast. And this particular model also makes sense. Do you have any questions about this?
I was just going to point out, it was not really a question, but I was just going to point out that when you get rid of the effect, or when you eliminate the effective age, it reduces the error bars on the original analysis.
Right. Right, exactly. Yeah, that's a good point. I should have probably mentioned that as well. Yes, when I was looking at the average activation in here, and you are looking at a one sample t-test, basically looking at the average activation across all of these subjects and whether that is significant or not. The significance is basically determined by contrasting the average activation by the residual between subject variance. So basically, you are constructing these error bars around the average activation, and you are trying to determine whether the 95th percentile of those error bars basically is above 0 or not. And because this model is not informed about age, basically all of this variability across subjects beyond that average level is going to be the residual variability, and that is going to be creating these large error bars. When you control for the effect of the covariate, basically, and look at the average activation at one particular level, and that level could be an a priori measure like 25, or it could actually be the average the age of your subjects, which is what you would what you do typically when you don't have an a priori idea about what particular level do you want to measure this, and you want to say, well, what is the average activation in these subjects at the average? I know that activation is kind of correlated with age, so I'm going to ask the question of what is the activation at the average age of this particular subject pool. So how do you do that? So basically you compute the average age for your subjects and you subtract that from your age variables, and that's what people typically refer as centering that variable. So you do that when you want to ask the question of what is the average activation at that average age level. And now, because the residual error is basically how the variability of all of these dots around this regression line, that is all going to be smaller than the residual variability across the total average, because you are controlling for you are reducing basically from you are taking into account this amount of variability that is explained by age that doesn't form part of your residual error. The only residual error in this particular model is anything that is not explained by this regression line. So basically that is going to be smaller than in this case when you have a model that is just a constant line, and anything that is not explained by this constant level is the residual error. So basically the residual errors in this model are smaller, and that means that the confidence intervals are always going to be smaller as well. And typically that means also the activation, the significance levels are going to be higher. That's what we were talking about the other day, for example, when we were talking about trying to control for other covariates of interest, because that to the degree that they affect the residual variability, if we explain them, we reduce the residual error and we increase the sensitivity. So basically this is a good example. Perhaps it's a little bit exaggerated because you don't see that tremendous amount of covariation between your measure of interest, which is activation, and that particular covariate like age. But if you have something like that, when you have a covariate that explains a lot of the variability, then by controlling for that covariate, even if you don't care about that, if you don't care about whether the actual activation is correlated with age or not, you just care about the average activation within this subject group. By controlling for that covariate, you reduce the amount of unexplained variability in activation levels, and you increase the sensitivity of this particular question. Does this make sense? Okay, so this is how you look at the effect, the average activation, while controlling for age in a single group. And controlling for age in a single group is just basically trying to account for that variability that might be unaccounted for when you just don't enter into your model. Then you go back. Okay, so what about difference between the groups? Okay, so let's say we have two groups now. We have group A and group B, and we want to look at the difference between the groups. And in here, I'm going to just, again, use age, even though I'm not going to put it into this model. But you have red dots, which are one group. I think it's group A. No, group B, blue dots which are another set of subjects. For every subject, I'm just entering like its age in the x-axis and its activation level in the y-axis. But I'm not going to care about age at this point. I'm just going to care about activation. So I have these blue dots, a group of subjects, and these red dots, another group of subjects. I want to look at the difference between the two groups. So how do you do it? You specify a model that has two covariates, and these are dummy covariates for every individual group. You have a group A covariate and a group B covariate, and then you enter a 1 - 1 contrast. And the reason why this is the case is because the group, when you have this design matrix, you have two columns in your design matrix, and you're going to get two regressors. The first regressor is going to measure the average activation within along the blue dots. So that's going to be the height of this horizontal line. So I don't see it very well, but I think it's 0.6 in this example. That is going to be basically the average activation within the blue dots. And that's going to go into the first regressor of your design matrix. And the second is going to be the average activation between the second group, basically this horizontal line, the height of that line. So that's this 0.5. So basically looking at the difference, you're looking at the difference between 0.6 and 0.5. So you're looking at this difference between the two groups. And that's what this contrast does. Basically it's looking at whatever you got in the first regressor minus whatever you got in the second regressor. Conceptually, that represents whatever height was in the first group minus whatever height was in the second group. That's basically the difference in activation between the two groups. And now you're asking the question of whether this difference is significant or not. So basically you're looking at the difference, and you're going to try to compare the size of this difference, the size of the difference between two horizontal lines, and the residual error, which is going to be the variability of the blue dots around the blue line and the residual variability of the red dots around the red line. That's what the residual variability is going to be. By comparing the size of the difference between the groups to the residual variability across subjects, you are doing basically and effectively a two-sample t-test, this is called. And you are doing testing whether the two groups have different means and whether that is significant or not. Does this make sense? so far? Any questions for this two sample test type of thing? So, okay, before I go into more complex stuff, let's look at a slightly different question. Let's say that you want to, yeah, I never mentioned, well, I mentioned very briefly the other day this, but right, remember that in addition to looking at difference between, sorry, go ahead.
No, I'm sorry, I was just unmuting because for no good reason.
Oh, okay. Do you have any questions, or do you want me to go on?
No, just I'm playing around with the screen here. I'm trying to get stuff the right size to see everything and also be able to unmute on a moment's notice. So carry on.
Yeah, let me see if I can, I should just make this a little bit bigger. So, well, let me see, perhaps I can share, you see my PowerPoint type of thing, right? With the next slide and everything, right?
Yeah.
Let me unshare this and share the other screen just for a second to see if that works better. Where are you? This one, let me check. Can you see the whole screen type of thing now?
Yep.
Or do you still see the preview view?
No.
Okay, cool. Okay, so just to make it a little bit bigger. Okay, so I was looking at that difference between the two groups, and that was the 1-1 contrast. Okay, another question that you can ask in the same way that we were asking before, whether the average activation was positive or not. So basically, you were computing these error bars for the average activation of this cloud of points and comparing at the 0 level. So basically, is this average activation positive or negative? When you have two groups, you can also ask that question. You can ask the question of whether any of the two groups shows different than 0 activation. Basically, in this case, if we are looking at the speech minus baseline type of contrast, we are looking at whether the speech minus baseline activation difference is significant either for one group or the other. So in here, we are looking at whether the difference between the activation levels themselves are different in one group or the other. In this question, in this case, what we want to ask is basically whether any of them is significantly different from 0. So basically, we could ask that question separately for every individual group, right? And we saw how to do that one sample t-test before. So we could ask whether the activation level in one group was significantly different from 0, and we could ask separately the question of whether the activation level, the speech minus baseline contrast, is different from 0 in the other group. How do you ask the question whether the activation is different in either one group or the other, or in two of them? So basically in any of the two groups. You ask them by creating this F contrast that basically concatenate the individual contrast that you care about into a contrast matrix. So instead of specifying a contrast vector like here, like if I just enter a 1, 0, I was asking the question about the first group. So I would be asking the question of whether this average activation was significantly higher than 0 or not. If I use a 0-1 contrast, I would be doing the same question just for the second one. So if I want to ask the question of whether in one or the other is significantly different from 0, then I just concatenate this and enter a contrast matrix, basically. And in this case, now what we are testing is not a univariate effect. We are testing basically a vector of two things. We are testing the average activation of this group and the average activation of that group, thinking of that as a two-dimensional vector. Is that different from 0? And that's what this test effectively does. And that could be different from 0 because one of the groups is different from 0. It could be different from 0 because of the two groups are different from 0. But the test just thinks of them as a two-dimensional thing. So in this case, it's just an F contrast, and that is in very general terms is an OR conjunction across the individual contrasts that you care about. So when you have a question that can be specified as something or something else, you just think about how you specify the contrast for the first something and think about how you specify the contrast for the second something and just concatenate those contrasts. And that will be basically the way to specify the metrics for that OR conjunction. Does it make sense as well?
Mm-hmm.
Okay. Okay, and the same thing can be if you have, let's say, multiple. Let's take this a little further, and let's say now that you have 3 different groups instead of 2, right? And you have 3 groups of subjects, and you want to test whether whether there is any difference between the 3 groups. So I haven't done a plot for that, but I should have, because it's not conceptually very different. So instead of these two clouds, you have three clouds of dots, right? And you have, let's say, blue dots, red dots, and green dots. They correspond to the three different subpopulations. And you want to, the actual question that you want to ask is whether the heights of those populations are different from themselves, right? So to each other. And the way to test that is basically by doing this type of contrast. And one way to think about it is by thinking of it. It's basically an extension of this type of OR conjunction that we were doing before. One way of thinking about whether there is any difference between those three groups is to break down the question into whether there is any difference between these two groups and is there any difference between these other two groups or in these other two groups, right? So you could potentially kind of like do pairwise difference between the three groups and do three contrast vectors, like a 1, -1, 0, a 0, 1, -1, and a 0 and a 1, 0, -1. And that would be, and then you just concatenate those three contrasts one below the other, and you would be asking the question of whether is group A different from group B. That's the first, that's the first contrast. Is group B different from group C? That's the second contrast. And is group A different from group C? And that would be the third contrast that doesn't appear here. And does any of these three things happen? And that's basically a way to specify whether there is any difference between the groups. And that's with the way that an ANOVA test actually runs these things. It's basically an ANOVA test in the case of three groups is an F test. It basically looks at this difference between the groups and thinks of those differences as a two-dimensional case, in this case, in the case of three groups, and tries to determine whether those two-dimensional things, which represents the difference between the groups, are zero or not. If they are zero, then there is no difference between the three groups, and if they are not zero, then there is some difference between the groups, and then it's up to you to determine which one is the difference between the group that it turns out to be significant. But the way to test it, basically, when you have three groups and you want to test the difference between any of the groups, is by doing this OR conjunction of the difference between two groups and the difference between the other. The typical thing that you might be wondering here is why I'm not entering that third column that I was also specifying, the 1, 0, -1 column. And the reason is because that is, there's two ways to explain this. One is that it's basically a linear combination of these two. There is no way that could be basically significant and none of these two be significant. Or perhaps the easier way to think about this is that the difference between the three groups in activation is actually like a two-dimensional. Yeah, that's a third way to explain it. Well, I don't know which one is the simplest thing to explain it because I don't have a good plot for that. But I think the two-dimensionality of the difference is perhaps the simplest one. Let's go for that and see whether that makes sense. So if you have three groups, you can look at the difference between A and B and the difference between A and C, and then A and C and the difference between B and C. Because there are only three groups, the difference between A and B and the difference between A and C have all of the information that you need to have. If I give you the difference between A and B and the difference between B and C, you already know the difference between A and B, right? So in terms of how many incognitas or variables there are in the to characterize the difference between these three groups, it's only two numbers that you need to specify to actually specify what are the difference between those three groups. And that's why you also need only two contrasts to specify whether that difference between the three groups is significant or not, because even though there are three groups, the difference between the three groups is a two-dimensional object. Basically, it lies in two-dimensional space. And this particular contrast, where you reduce that to two questions across the difference between two groups, is a totally equivalent manner of asking that question as if you choose any other two combinations. So I could have chosen, for example, like a 1, -1, 0 contrast and a 1, 0, -1 contrast, and that would give me exactly the same statistics. Or I could have chosen like a 0, 1, -1 contrast and a 1, 0, -1 contrast. I would still get exactly the same F test because they are all asking the same question, which is there any difference between the three groups? Does it make sense so far?
Sure.
Okay. Do you want to make a guess how you would do for four groups? Basically, if I want to test whether there is any difference between four groups, how would you go about doing that? Yeah, that's a good one. Okay, so can you read that into a contrast, into telling me which contrast those are without typing in MATLAB?
That's going to be my next move.
Quickly, somebody open MATLAB.
Is that like a 1, -1, 0, 0, 0, 1, -1, 0, and a 0, 0, 1, -1.
Exactly. Yeah, that's perfect. Yeah, and exactly the same thing happens for n groups. So basically, if you have 10 groups, you have to enter basically 9 vectors, contrast vectors, that represents the difference between two pairwise comparisons between the groups, and that kind of like uniquely defines all of the difference between the 10 groups. So in the case of 3 groups, you have a 2-dimensional vector. In the case of 4 groups, you will have like a 3-dimensional vector. So you would specify 3 contrasts. And in the case of n groups, you have n-1 rows in your contrast vector. And typically just enter 0, 1, -1, and then 0, 1, -1, 0, 0, 1, -1, and so on. Okay. And that's basically a one-way ANOVA, right? Because we are looking at just one single between subject factor. If you're familiar with like ANOVA nomenclature, we have just a single factor, which is this group effect, but has 3 levels because we have 3 groups. And you are doing an ANOVA, you are looking at the main group effect. Are there any difference between the 3 groups? Okay. Okay, so now let's combine these multiple groups with the H thing, with the covariate thing that we were talking about. So now let's say we have 2 groups and we have a covariate, which is kind of getting closer to what you had solving this example, right? With the motion and the 2 groups. So now it's kind of like the same as we were doing before. We have this population of red guys and blue guys, and the y-axis here represents the activation, and the x-axis represents H. And now, before, if you recall, we were just looking at the average across all of the blue guys as a horizontal line, and looking at the average of all of the red dots as a horizontal line, and looking at that difference. Now we're going to take into account H. And by taking into account H and doing it this way that I'm going to talk about in a second, we are just assuming that the effect of H is constant across all of the groups. So we are going to assume that the slope of the effect of H, basically how activation changes with H, let's say that is constant between the 2 groups. It's going to be the same. So we want to estimate something like this. We want to estimate some line that is not necessarily horizontal. It might be horizontal, it might be positively inclined or negatively inclined, that represents the way that activation changes with H. And then on top of that particular line that we were also modeling here, right? Remember, so before we were doing something like this, we were doing a line across all subjects that represents how activation changes with H. Well, we are doing the same now, but we are breaking that line into 2 groups. We are allowing that line to have different heights for one group compared to the other one. We are not allowing that line to have different slopes, right? And that's why this is, we will see that example later on. But in this example, we are allowing that line, we are forcing that line to be constant in a slope across the 2 groups, and we are changing the intercept. We are allowing this line to have a different y-intercept than this other line. So basically, we have these 2 horizontal lines. Each of them are going to have different heights potentially, and we are going to fit that type of model to the data. And the way to do that is basically by specifying this type of contrast. You specify group A, which is this dummy-coded covariate for one group, group B for the dummy-coded covariate for the second group, and then H, which is going to be just your H covariate across, just a single covariate across the 2 groups. And in the same way that before H was kind of measuring the slope, now H effect is going to measure the slope of this line, again, in units of activation per year or whatever units your covariate has. And then group A and group B, in the same way that the all subjects term before, in this case, the all subjects, the all subjects effect, remember that it was capturing kind of like the y-intercept of this line, basically the height of this line when it intersects at the 0 level of the covariate. That is going to happen again here, but now you're going to have 2 y-intercepts. You're going to have a y-intercept for a group A for these subjects. So basically where this red line intersects this 0 axis, and then the same thing for the blue line, where this blue line intersects this y-axis. So that is going to go into the group A regressor, then the height of the intersect for the other group is going to go into the group B regressor, and the slope of those 2 lines, which is shared across the 2 groups, is going to go into the H regressor. So because you have this type of model, you can do the same things that we were doing before. You have these 2 y-intercepts that are going to be separated the same distance as the distance between these 2 lines, right? So if I just look at because I'm assuming the covariation with H to be the same, it doesn't matter where I draw like a vertical line in here, the difference between the 2 lines is going to be the same because those 2 lines are parallel, right? So if you just want to know the difference in height between those 2 lines at any arbitrary H level, you can ask that question by looking at the difference between the y-intercept of those two lines. And that's basically creating this contrast, this 1 minus 1, 0. This is looking at the difference between the activation of the two groups while correcting for H. And the tricky thing in here is, and I'm doing that kind of like very exaggerated in this plot, but I'm doing that on purpose. That doesn't happen so severely in real data. But I'm trying to show something in here. Remember that in this plot, I had I think if I did it correctly, the same dots as I was doing here, right? So I have these blue dots and these red dots. These blue dots are higher than these red dots on average, right? But they are also to the right in this compared to the left dots. So they are basically an older population that has higher activation, and this is a younger population that has lower activation. But now that I'm using the same clouds here, basically the same dots, but because I'm now controlling for H and I'm trying to take into account how activation correlates with H, and in this example, activation, I'm making so that activation increases with H. Now, if I look at the difference between these two lines, I get exactly the opposite effect, directionality of the effect that what I was doing before, right? In this example, the activation was higher in the blue group compared to the red group. And if I look at these lines, now the activation is higher in the red group compared to the blue group. So what does all mean, basically? Why is it different? And how do we interpret those things to be different? The thing is basically that this is just looking at the average activation between the two groups and looking at whether activation is higher in one group or the other. That is very simple to interpret. This thing is actually saying, well, we are going to assume that that activation changes with H, and we are going to assume that that is constant across all groups. So I'm going to try to ask the question whether the activation is higher in one group or the other, but at the same H level. I know that the H is larger for this blue group compared to the red group, but I'm going to try to look at what the average activation would be for this blue group at one particular high age level, for example, at 30 years, and I'm going to look at the average activation of these guys at the same level, let's say at, again, 30 years, and I'm going to compare those average activation at the same age level. And that's what this basically tells you. This contrast when controlling for age is looking at the difference between activation between the two groups at the same level of the covariate. So basically, if you have a covariate that is H, you're asking the question of whether the two groups have different activation when comparing the two groups at the same H level. If you have another covariate like motion we had before, and you're looking at the difference in activation between the two groups controlling for motion, what you're doing there is basically asking the question of, I know that one group may be moving more than the other group, so I'm asking the question, if I just extrapolate and I look at the average activation of the two groups at the same level of motion, is the activation higher in one group compared to the other one? And that's what this type of comparison between the groups while controlling for a covariate allows you to do, basically. Does this make sense so far?
Mm-hmm.
Sorry.
That's nice. It's nice.
And do you have any questions for this, or do
Really clean. Jason?
No, I think it's good. I mean, that's one of maybe we can take this this example that we just went over. One of our, someone that enjoys writing a lot, and swap in, say, the motion, and talk about that and how, because this is a great way to understand what we've been talking about in the last few lab meetings of how to control for something without actually removing, like if the motion is, well, but maybe we could talk about that, Alfonso. Like if the motion's correlated with say the activation, right? Mm-hmm. This is a way to remove the variance due to motion, but still maintain we can still assess the mean activation level between the groups.
Exactly right, and I'll let me. I think I have an example for that as well. Let me check. No, I don't. I can talk about it in this case as well. So That's a very good point as well, because in this case, I'm asking the question of what is the difference kind of like between an activation between the two groups at the same. I'm going to switch, and whenever I say motion, I'm going to set up, whenever I say age, I'm going to assume that this axis represents motion from this point on. So that is a little bit closer to what we are talking about in general. So let's say in this case, the two groups have actually different amounts of motion, right? And we want to correct for that in the sense that we want to compare them at the same motion level. Kind of like imagine if they had the same amount of motion. And magically, or at least statistically, and we want to compare them at that level. But sometimes you don't want to do that. Let's say that you really don't care about that because for example, we were talking about the other day where we really didn't want to control for the difference because that difference was actually part of the effect that we care about. So.
Oh no, I thought it was well, it was speaking rate was that there was a lower speaking rate during the rhythm condition than during
right speaking rate. Okay.
That's within groups contrast. I don't know if that changes anything.
Right. No, but I mean it makes that's what I wanted to talk about in this example actually. So let's say that this is a speaking rate, but let's say that that difference between the two groups in a speaking rate is meaningful to us. So basically, we don't want to do this. When we do this comparison, we are basically contrasting. We are trying to correct for the potential difference in a speaking rate. Let's say that these guys are let's say this is actually speaking rate. So these blue dots in here are speaking faster and the red dots are speaking slower. Well, let's do it the other way because I want the activation to be higher basically for the faster that you speak. So let's say, do you have a measure that is kind of like the opposite of a speaking rate?
Speaking rate. Syllable duration.
Okay. So duration. Yeah, syllable duration. Okay, that's perfect. But let's say that. Am I assuming correctly that typically you would expect the speaking rate to be positively correlated with activation, or perhaps not? What do you think? Do you know this better? You probably have more experience on that than me. So.
Probably depends on where.
Right, because
I would say it's all rampant speculation.
Okay, so let's say this is duration, and let's say the longer the duration, the more activation you have, just for and I'm going to talk about these numbers as if they represent duration. So we have these subjects that are speaking slower, the blue dots here, and we have these subjects that are speaking faster, the red dots. And we know that the ones that are speaking slower are going to have more activation, just because we know that happens. The slower that you speak, the more activation that you have, because duration is, I don't know, because you integrate a longer window. So for whatever reason, we are speculating for that to happen. So we could ask the question of trying to compare the activation between the groups while controlling for that effect. So basically, imagine that the actual duration of the two groups was the same, and what was the difference between activation levels of those two groups, whether the activation was higher in one group or the other at the same level of duration. Or perhaps we don't want to control for that, in the sense that we still, because I don't know, perhaps the duration is actually something that we expect the region that we are interested in to actually show an effect that somehow corroborates with that difference duration. If we remove the duration, we are removing the effect that we care about, because perhaps, I don't know, Jason, help here. Can you give me an example of why, in some example where some region we would want to actually not control for duration because that would remove that portion that is significant to us?
Well, I don't know. I mean,
I was just the suggestion that Frank made was that, well, maybe rhythmic speech is duration is intrinsically part of rhythmic speach. That slower, I don't know. That was sort of what he was arguing, is that the effect is due to combination, and that if you get rid of one, you might get rid of the effect of the other. Maybe that's a bad example, actually. But
okay, but that's a relatively good example. Let's say that in this case, we kind of like know that this goes in this direction. So basically, because that, and we know that these guys that are speaking higher might actually have higher activation just because they are speaking slower, which is totally fine. But we want to ask the question of whether that is actually happening or not independent of this, but we still want to control for that. So basically in this plot, we want to basically draw those horizontal lines, but now we don't want to compare those two horizontal lines in height. What we want to do is basically look at the average of the blue line, like the kind of like the centroid of that line, and look at the centroid of this line in here, and compare the average of those, the height of those two things. So basically it's something like what we have here, basically. So the centroid is going to be here. I don't know. Do you see my mouse moving when I do this?
A little bit.
When you,
Yeah, it kind of goes on and off. Okay, but basically you will have like a centroid somewhere in here, basically, and then you will have a centroid somewhere in here. And in this comparison, you are asking the question of whether that centroid is higher in the blue in this group compared to the other one. But this actual comparison, all of the variability that just correlates with duration in this case, is acting against us, right? Because this difference perhaps is small compared to all of those differences that just have to do with duration. And we want to control for duration in the sense that we want to remove that variability that just correlates with duration, this whole slope of these things. But we don't want to control in the sense that we still want to compare the average of one group compared to the average of the other. So basically, coming back to this, we want to be able to trace those lines. So we explain actually the variability that correlates with activation, but we don't want to compare these two heights, basically. We want to compare these two centroids. So it's a mixture of the two cases. We want to compare these two heights, the same thing that we are comparing here, basically the height of that difference between those horizontal lines, but we want to do so in a way, that actually draws this kind of like a slope line so that the amount of activation that correlates with duration is actually accounted for. That doesn't count as residual variability. That counts like explained variability, explained by just duration. And we want to look at whether basically we want to compute these centroids, but getting smaller residuals, because we want to take into account all of the variability that is actually taken into account by just correlation with duration. Does it make sense conceptually what the idea would be for that comparison?
Yeah.
Not quite. So I don't know.
Is it valid to do that? I mean, well, I guess it depends on the specifics of the question, but.
Right. I mean, so let's say that we have this fit actually, and we are going to model this fit by a centroid of the cloud and a slope that is going to be the same. And instead of modeling as intercept of the y lines, we are going to model it by three numbers. The first number is going to be the height of the average of the blue cloud. On average across all of the subjects. The second, which is going to be somewhere around here, which is going to be exactly at this height, right? This 0.6. So that's going to be the kind of like dot that we're going to plot here. And then we're going to model these guys by the average activation of these guys, which is going to be around 0.5. And then we are going to model the slope of that by a different number so that we can explain basically the same data that we are explaining exactly in this model, only that we don't want to ask the question of the difference in heights. We want to ask the question of the difference in centroids, right? We want to ask the question of whether the centroids of these two clouds are different in height, as opposed to asking the question of whether these lines that just fit these two clouds have different in heights. Do you see how those are two different basically questions in terms of, those are perfectly valid questions in terms of the geometry of the data, right? We have some clouds of data. We are feeding the data through these fits, basically in this case, in the other case, horizontal lines, in this case, lines that have the same slope across the two groups. And we are asking the question of whether, we could ask the question of whether the heights of those two lines are different, basically, or we could ask the question of whether the centroids, the heights of the centroids of those two lines are different.
But if there's a difference in the centroids, that could be due to differences between the conditions or groups themselves, or it could be due to a general trend where if you have greater speaking rate, then you're going to have higher activation anyway, and so it would be difficult to dissociate those things.
Right, exactly. So you could have some scenario like this, for example, where this is, so if we could ask the question, in this case, the blue line centroid is higher than the red line, right? But it's higher in a way that is strange because it's not higher than, it could be higher than, as in higher above the red line itself. It could be still higher and below the red line, like in this example, or it could be just about the same, like continuing the red line, right? It could be those three scenarios.
Right.
In this case, or it could be lower. I mean, or it could actually be the same height. It could be just the blue line lower than the red line, but the centroid of the blue distribution to be about the same as the centroid of the red distribution, despite so basically, despite the duration being higher in this case, and duration being correlated within each group with activation, you could find that the actual activation levels between the two groups is about the same for whatever reason that happens, right? And you could so it's perfectly valid to ask the question of whether those heights are the same or not, and whether those two lines are the same or not. It's just that the interpretation is totally different, right? And the thing that before we get to the interpretation, the thing that I just want to get is kind of like numerically, there is a slight different thing, different sensitivity as to when you just care about the centroids of those two populations. The sensitivity of this test is always going to be smaller, well, not always, but almost always, than the sensitivity of the same test when you look at the difference in height of the centroids, but take into account age. But because to the degree that age correlates with something, the residual error is going to be smaller. So basically, the error bars that you get for every, so something like this example here, the error bars that you get about the height of each individual group are relatively large in this case because they anything that is not explained by the average level of activation goes into the size of the error bars. But if you do the same thing and draw an error bar about the size of the centroid, in this case, because some portion of that variability across subjects is actually explained by duration, you can get a better measure or a better sensitivity to the average activation within that group. So basically the error bars are going to be smaller in here, even though they are measuring the same thing. You could actually ask the question, and I'll show you in a second how to ask that question, but basically you could ask the question about, in this type of fit, whether the centroids have the same height or not. But you would be asking it to the degree that this plot is right, so basically to the degree that the activation is actually correlated with duration, like in this example, it's always going to be smaller error confidence intervals for this type of plot because you have more things that you are taking into account, and you have more of the actual activation that you are explaining with your model. So the error bar of the height of those distributions is going to be smaller. So when you compare them, you can have higher sensitivity to compare. So basically, to ask the question of whether the heights of these centroids are different, you have more sensitivity in this case than in this case when you don't control for age. Does it make sense? Okay, I don't know if I'm confusing you guys at this point.
I'm trying. When you say this, so when you go back to the other slide, we're looking at that top plot. Where you're just looking at the mean of those two clouds of points.
Right.
When you go back to the other one, we're not really talking about the top plot anymore.
Right.
I'm not talking about the middle one either. We're talking about
right. I'm talking about something else, right? That it would be looking at the. That's. I should create it. Let me see. Well, let me see if I can. Well, it's going to be a bit tedious to create it now because I don't have a good mouse. So sorry about that. But it's basically something that is basically plotting. I don't know how to explain. Imagine this blue line that has a dot in the center of the blue line, and imagine the red line that has a dot at the center of the red line.
Yep.
The height of this dot is going to be the same as the height of this line.
Right.
The height of this dot in the blue line is going to be the same as the height of this blue line.
Yes.
But you could ask the question of whether those two dots that are not represented in this plot, but we are kind of like imagining right now, have different heights or not. And asking that question is basically asking the same question as you're asking here, which is basically whether those two heights are different or not, because the height of those dots were the same as the height of this line. So basically, you're looking at the same effect. You're looking at the difference between the centroids in height of those lines, but you are comparing it to something different. In this case, you are comparing that difference in height in the centroids of the population to the residual variability and unexplained variance in activation across subjects. And unexplained basically means anything that is not explained by the centroid height. And in this case, unexplained is everything that is not explained by either the centroid height or duration. right? So there are less things that are unexplained in terms of the residual variance. So when you compare the same size, which is the difference of the heights, to that unexplained variance, you're going to have a higher t-statistic typically for this type of test, because you are removing some portion of the unexplained variance, even if you are measuring the same exact thing. So the thing that you are measuring in this imagined case is still the difference between the centroids, the height of those centroids, but you can compare that difference in height to something. In the first case, the variability in activation within each group, and in this case, the residual variability within each group after discounting anything that correlates with age. Does it make sense?
Sure.
Yeah.
Okay, and the way to actually do that, I mean, I should have a different test, because a different basically line here to explain that. But it's exactly the same thing as we are doing here, but by changing how you center this age covariate. Because remember that that this all works because the age the group A and group B is going to be conceptually measuring the y-intercept of these lines. So basically, when you compare the y-intercept of these lines, you are looking at the difference in height between these plots, right? So how you would adapt that to make sure that you are not comparing that difference in height between these two plots, but you are actually comparing the difference in height between the centroids. Well, one simple way to do that will be to get this blue distribution and move it to the center of the red distribution, at least horizontally. Don't change the height, but move it horizontally so that the centroid of the x-axis of the blue dots is exactly at the same position that the centroid in the x-axis of the red distribution. So basically, you move the distribution horizontally of the blue dots to the left until it matches exactly at the same level. And now the difference in height between those two y-intercepts actually measures the difference in height between your centroids. Because you just move horizontally the line, you are still measuring the centroid of the exactly the same height, right? But because you place the centroid at the same height of the two, at the same x-axis of the two distributions, now you are comparing them not at the same age level or activation level. You are comparing them at the average level of duration or age within each group separately. So you're asking the question, let's go back to age for a second. You can ask the question, is the activation of the average guy in this group, even if he is 30 years old, is that higher or lower than the activation in the average group, in average guy in this group, even though he might be 20 years old? So you're comparing kind of like an average guy in this population, and the average is 30, compared to the average guy in this population, even though his average is 20. You just move that 30 to the 20 so that you can compare those two things at the same level. That's kind of like graphically how it works, and mathematically how it works is basically by changing the age covariate so that it's centered separately within each group. So basically, instead of taking the age covariate and center it at whatever level you care about to kind of like move the y-axis to whatever level you care about, you center it separately within each group. So you are effectively kind of like shifting this distribution of dots horizontally, but only differently by amount in one group versus the other. So you are keeping one constant, for example, or moving let's say, if you center them separately, what you are doing is kind of like moving the red distribution so that the centroid is at the 0 level. So basically it intersects this axis. So you are moving this whole distribution to the left so that it is exactly the centroid, it cuts exactly around this line. And then you do the same thing for these guys. You move the distribution of blue dots to the left so that its centroid is also at this y-intercept. So now when you compare the y-intercepts of these two lines, you are actually comparing the height of the centroids of those two distributions. Does it make sense? And mathematically, it basically works by taking the age covariate and centering it within one group and then centering it within the other group separately.
But it would still be the same covariate. You would still
It would still be, exactly, it would still be one single covariate. It's only that you have centered them separately within each group. But it still would be one covariate, because the case of having two covariates is basically this thing below where you allow different slopes. And I'll talk about that in a second, but not yet.
And so, what's the summary interpretation if you find a difference there?
Right. So the summary interpretation is the same as this, basically. You are saying, you are asking the question of whether the average activation within one group is different than the average activation on the other one. And you are saying, I know that some level of activation correlates with age. I want to take that into account to kind of like reduce the amount of unexplained variance, but I'm still asking the question of whether the activation on average is higher or not in one group compared to the other. You're still controlling for age, but not controlling at the same level of age. So kind of like interpretation it works in the same way as this, basically. It's only that gives you higher sensitivity because you are reducing all of the variability that correlates with this, basically.
But you're also sort of just selectively correcting for age, because you're correcting for the component within each group without acknowledging that there's an effect across if there was an effect across all the participants that this effective age, you'd only be getting rid of the effect of within group effect. And so we just have to know that when we're talking about it. And I mean, it's in some ways it seems a little bit like you could fudge the numbers to make it like to just get rid of one effective age but not the other effect, which would change the results to whichever way you want. But I guess it all depends on what your question is.
Right. I mean, it depends a lot on the interpretation. I mean, it's important to understand kind of like what it's doing mathematically to kind of like know what you are measuring, but
Right.
it's not, but it's perfectly valid in some scenarios. So it's a perfectly valid question in some scenarios, but it has to be one particular scenario for that contrast to not be, so to that effect. So let me say, think of one scenario.
Yeah, so here's an example that might actually make sense. So if you have stuttering severity, as you were looking at before. So in the case of stuttering severity, all of the control participants are at one level, at 0, say, and the other participants vary. They have perhaps some slope, where as you get increased severity, there's greater activation, say. And if you were to just get rid of the effect of the effect of severity separately for each group. Well, in one group, it doesn't actually count any of the differences, but in the other group, it does. So you're shrinking the error bars on that other group.
Right. Okay. That's a very good example. So imagine, for example, that it's going to be slightly more similar to this, but imagine that something like that. So imagine that these red guys don't. So let's say this is severity, and this severity only applies for the blue guys in this case. For the red dots, they don't have severity values. So you can put them. So basically, they are a cloud of heights, but they don't have any X position. You can put them wherever you think it makes more sense. I mean, you could say, well, perhaps it makes more sense to talk about severity 0 for these control subjects, right? So you can think of those dots are being here, basically, in this, forming a cloud of points here vertically. Or you could think, well, perhaps they don't make sense to be 0. They would need to be negative, or they would need to be 50, or you don't know exactly where to put them. So one way, so because you don't know exactly where to put them, you could ask the question perfectly valid of what is the average of these guys and what is the average of these guys, taking into account that there is some serious amount of correlation between activation and severity, but you still want to compare just the average severity at the average severity level for this group and compare it to the average activation within the controls, even though that level might not be meaningfully corrected by severity because there is no way to apply a severity number to these guys. So in that case, that would be a good example. That would be an example where you want to like have this distribution of dots that you don't care about the X value of these guys because it doesn't make sense for them to have an X value, basically a severity value. But you still care about the average activation level of these guys, and you still care about the average activation level of this other group. But you want to do that comparison at the average level. You don't want to compare it at the 0 level of the covariate because that would be meaningless, or that would be making the assumption that the subjects are actually at the 0 level of that covariate, which you don't want to make, right? I mean, you could have another covariate where you want to make that assumption, and you could say, perhaps I want to compare what would be the activation level of an ideal patient that has 0 symptoms, right? And you could compare that to your controls and say whether that is whether there is any difference between that ideal patient and a control. But this is not the case that we want to do here. You want to compare actually your patients as they are to the controls, but you want to take into account that patient activation covariates with severity because there are many things that covariate with severity, including like I don't know, attentional levels and how much the subject is going to get anxious in the scanner and many other things that might not be then I don't want that. There is no meaningful way to make a valid comparison with the groups. So you still want to look at the average activation within the patient group and the average activation with patients, still controlling for the amount of activation within the patients that correlate with activation with severity, but still looking at the average activation level within the patients. Okay, so for that case, you would do exactly something like that. You would enter.
Zero level, right?
Yeah, 0 for the controls, the actual values centered at the level of that group with the patients. So basically, it's basically assuming that you give them for all the controls and numbers, let's say 0, and then you center separately within each group. So the controls end up having all 0 values, and the patients end up having whatever values they had, but centered at 0. So the average within the group is within the patient group is actually also 0. And then you are doing this type of comparisons where you are looking at the average activation, the difference in average activation, controlling in this sense by severity. But not in this sense as we are plotting in this scenario, right? Make sense?
Right. Yep.
Okay. And yeah, that would be an example of. I mean, it would be a little bit more convoluted because in that case, it doesn't make sense for the controls to actually have severity values. But I'm sure we'll run out into another example where we have a covariate that is actually meaningful in the two groups, but you know that it kind of correlates with activation, but you still don't want to subtract or control for that because you think that some portion of that difference is actually the difference that you care about. It's kind of like an after effect of the difference that you want to detect, which is like a mechanistic difference. Perhaps the patients are doing something different. I mean, the brain is behaving differently than the controls, and that difference is actually causing both the difference in activation and the difference in your covariate. And it's not that the difference in the covariate is actually mediating the difference in the brain behavior and activation. So I mean, that's perhaps a good way to go about it. I mean, to think about the difference between a mediator variable and one of these like Y type of source variables. So you can have something that acts as a mediator, for example, in this case, H, that perhaps the difference that you are looking at the activation between the two groups is actually not true difference. It's just because in this wouldn't be a good example, but anyway, if you see an activation difference between the two groups and you know that the two groups have difference in H and you know that H correlates with activation, you might say, well, I'm looking at the difference in activation between these two regions, between these two groups, but perhaps it's just mediated by H. It's just caused by these two groups having different H levels. So that when you want to control for a potential mediator variable that is actually causing is kind of like placing the middle between the difference between the two groups that you care about and the activation difference that you care about, then you control it in this way. You control it by entering a certain covariate and using a single covariate and centering it at one unique level across all of the groups as opposed to separate levels. In some cases where you think of that covariate not to be like a mediator, but to be something that is perhaps an additional outcome variable. So for example, you can say, let's say that the difference between the patients and control is causing this mechanistic difference that you can actually see in difference in activation, but it's also causing in an unrelated way some difference in anxiety levels because of some totally different thing. And you know that the subjects the patients are going to be more anxious than your subjects, and you have actually gone ahead and measured that anxiety level, and you know that activation kind of correlates with anxiety because that many things correlate with anxiety, but the thing that you care about, which is the mechanistic difference between the brain in patients and controls, you think that is kind of like a root cause of both the difference in activation that you're going to see and also the difference in anxiety that is kind of like an end effect. So you don't want to control for that difference in anxiety between the two groups. You want to take it into account as a covariate, but not by controlling for the difference between the two groups in that measure. Does it make sense a little bit? Or? I don't know, we'll probably run into a few more examples of actual things that we care about where a variable have different interpretations. And depending on how we want to interpret it, we will use one method of controlling for it or another one. Sorry, go ahead.
I just wanted to jump in and say, we've gone through these examples a bit before, and these are really handy. And I find one where we have the concrete example here it's much easier for me to really wrap my head around
Yeah.
the significance of each. So what I'm wondering is if
I should add that other example as well, right?
Well, yes. So what I'm wondering is if we should just go through the examples that you have, because I think there's another slide of them, right? And
I
then,
have.
like, just to get that part down, but then use our maybe we could have Saul, you'd be up for this.
Sure.
Elaine, I'll help chip in, but for us to try to tease apart the different real world issues, like the real world examples that we're coming up with here, and make another set of slides where maybe we actually have some greater amount of explication on them, and so that we can refer to those examples, because I think this becomes the potential here for a really powerful way for us to wrap our heads around the statistics, and a much better way for us to explain it to new people. Well, not even just to new people that would be using it, say they're coming into the lab, but for writing up our papers would be really handy.
Yeah, I agree. It would be much simpler to explain a few of these subtleties if I had that actual example that I'm trying to talk about, like a draw.
Well, one of the things, just as an aside, there's a tool that the QDEC tool that comes with FreeSurfer. I don't know if you're familiar with that, Alfonso. It's basically trying to do this. Like you run all of your contrasts or whatever. You know, it could be functional MRI. It could be, you get some sort of values on the surface, and then you can run all these contrasts, and it really tries to hold your hand through it. But one of the things that's really cool is that as you try to you generate your design, and you hit a button that says go. One, as you're generating the design, it sort of like teases apart some of this information, and then when you hit go, it runs it, and then when you can click on each vertex, and it'll make plots look very similar to the ones that you have here. So it's sort of like it kind of holds your hand through the process. And I don't know that I mean, you know, in an ideal world, that would be cool if that was part of FL or Con maybe, but short of that, it was just a demonstration of how powerful having that built in can be, because the tool is sort of limited, except for this nice piece at the end where when you click on it, like when you run it organizes the results by the question that you're asking. So it's like, or do you want to look at the main effect of this while controlling for this? You click on it. So that's how you access the volume that you're looking for. But the plots are really handy. So you can see what the question is, and then you can see a plot of it divvying up for each vertex. So if you have like different groups, or it color codes them like you have here, and then it has like, you know, there's a age on one axis and height of the activation on the other. Anyway, that's just I won't spend too long saying that stuff's cool. And
that's cool. I definitely would like to see. I was not familiar with that, but I definitely like to see that. And there is a little bit of that functionality kind of built into Con, but it's still not kind of like accessible directly, at least within FL scripts, because that's mostly second-level analysis, which we are only like very marginally touching Con functionality. We are not, but I could potentially do that. At least, I mean, it gets a little bit more complex. The more complex the designs are, to kind of like visually represent what you care about. But it's always at least possible to do so in a way that at least for simple designs is more intuitive to kind of like interpret what you are looking at. And as the designs get a little bit complex, it becomes a little bit more complex to kind of get a measure of something graphical that corresponds to the difference that you are actually evaluating. But I'm definitely interested in seeing how FreeSurfer does it. So yes, at some point we'll if you don't mind, let's meet.
Sure.
And you can walk me through that. I would love to.
Okay.
Okay, but for now, I'll take your guideline here, and I'll just go through these examples, and then these other kind of like more sophisticated examples that are actually important for us, at least for this type of covariate control. Will kind of leave for later, and so that will give me a chance to create additional plots for that, or we all kind of like together think about examples that we can just base our plots or our discussions around. That will ground us a little bit better than right now that we are just talking about very abstract concepts and scenarios.
And one way to do that would be, we have 3 studies going now that are using this, and we could just look through, like after you go through the examples here, we could then go through the configuration files and say, okay, that's this one, and then it's, oh, that one's not there yet. That's
right. That's a good point. I'll do that, and I already took note for this particular kind of like covariate control scenario, which is very interesting and is not covered by any of these plots really. But I'm sure we'll run into a few more examples that I haven't quite covered, and it will be interesting to have a more kind of like grounded example of our data in mind as well for all of this. So cool. Okay, so I'll continue then with this. Are you up for that?
Yeah.
Okay, that sounds good.
Okay. So we'll look at that difference between the 2 groups controlling for H, and we were looking at that type of control that was actually trying to discount any difference between the groups that could be better explained by difference in H between the 2 groups, right? So in this case, we are trying to say, well, perhaps the blue distribution is higher than the red distribution, but it's mostly because the H are also higher, right? This is an older population, so perhaps that higher activation that we are seeing in this group is lower. And if we actually taking that into account and kind of think of the natural progression of activation within H, we find that there's actually lower, like in this plot example, the activation that we find in this older group than what you would expect. Even if it's higher than the other group, it's perhaps lower than what it should what you would expect the activation to be at that particular H level of this group, right? If the 2 groups were the same or homogeneous. So that's kind of like the question that you are doing this on for this type of control. When you enter this H covariate and you try to compare the 2 groups at the same H level. And because the H covariation, you're assuming it to be the same. This is like an a priori hypothesis. You are making that assumption rather than a hypothesis. You are making the assumption that the covariation with H is the same between the 2 groups. Then it doesn't matter at what level you kind of compare the 2 groups, at what H level, the difference between the heights of those lines at whatever H level is going to be the same. So it doesn't matter whether I look at the difference in activation at age 40 or I look at the difference in activation at age 20, because I'm assuming the activation to have the same slope, the difference is going to be exactly the same at any level. So that's why we don't have to worry about at which level we actually center that H covariate for this particular contrast, because it doesn't matter where we center it, we're going to get exactly the same results because the difference in height is the same at every H level. Okay, and well, this we saw before, and this is, but in some cases you do want to care about the centering of that covariate, and this is when, instead of looking at the difference between the activation between the 2 groups, which is constant across H, when you actually care about what is the activation level of one group at one particular H level. So if I want to ask the question, what would be the actual activation within this blue distribution, this group A, at the level of at age 25? How do I know that? How do I know the height of this line at age 25, the activation level for age 25? I just center H covariate at level 25, so I subtract 25 to all of the H levels, and then this contrast, just looking at the y-intercept for this particular line, because we moved that so that the 0 level of the covariate is at age 25, that y level is going to directly represent, that y level is going to directly represent the height of the average activation at that level at age 25. Right, next. Okay, so the subtlety here comes when, well, in some cases, this is fine for all of the scenarios that we show, but in some cases you actually want to test whether the actual H is covariation is different between the groups or not. We are making an assumption that is the same, but sometimes you want to actually test that assumption. Can I test that assumption? Or sometimes you do care about that, and because that is it's not only just to check an assumption, you sometimes actually do care about whether the correlation between one variable and activation is different between the groups. So you could ask the question, well, I don't know, perhaps I know that activation is going to be lower with H, so just the opposite of what I'm seeing in this example, right? Imagine I know that activation in some particular region is going to decrease with H because that's just the natural thing that happens with H in this particular region, but perhaps it decreases with H faster under this particular condition, right? If we have these patients, the decrease in activation with H is faster than what it is in the normal population. And I want to compare that. I want to look at what is the actual rate of decrease of activation with H in one group and compare that to the rate of decrease in activation in this other group. So basically, graphically, that means that you want to fit lines to the H by activation clouds of points, and each of them is going to represent the how activation is changing with H within each of the groups, and you are going to test whether the slopes of those lines are different or not. So how do you go about doing that? You do that by adding an additional covariate. So now you need 4 covariates because conceptually you have 4 things that you are measuring. You are measuring the y-intercept of each of these lines, so 2 things, and you are measuring the slope of those 2 lines, which are different. So you have 4 things that you are measuring. So this group A covariate is just the dummy covariate group A covariate that we had before, once for that group and 0 for the other. This group B is the same thing for the other groups, 0, 1, once for the group B and 0 for the other subjects. And now you have these H groups, H covariates that are specific within each group. So you create a covariate that only applies to subjects within group A, and that you have the H for those subjects and make it 0 for all of the other subjects. And you create another covariate which is H for the other group, and you create a covariate that has H for the group B and has 0 for all of the other subjects. And now you enter these 4 covariates, and basically this is going to be, you are going to get 4 regressors. This is going to be the y-intercept of the blue line. This is going to be the y-intercept of the red line. This is going to be the slope of the blue line, and this is going to be the slope of the red line. And the slopes are the same thing as before. They are in units of activation per years in this case, or activation per units of your covariates in the other case. So how do you test whether the slopes are the same or not? You just enter a contrast 0, 0, 1, -1, because this is going to encode the slope of one of these lines, and this is going to encode the slope of the other one. Just contrasting those 2 values tells you whether the slopes are different or not. So this is a way to test whether the change in activation with H is different in this group or in this other group. So kind of like conceptually, this is like an ANCOVA, and you are looking at the interaction effect of, you are looking at the interaction effect of group by H, by your covariate. You are looking at whether the difference, whether the covariation with H is different between the groups. Does it make sense? Sorry, go ahead.
I think you already said this, but just to be extra sure. So here we're just looking at the difference between slopes, not the difference between intercepts.
Right, exactly. So this is just looking at the difference between the 2 slopes. You are asking the question of whether the rate of change in activation with H is different between the 2 groups.
Okay, got it.
Right, and that is also a very interesting question, because let's say that we do care about the difference in intercepts. That becomes a really complicated question, not mathematically to ask, but to interpret correctly, because you saw that in this case, when we look at the difference in the height, it doesn't matter where we carry it, right? If we look at these 2 lines at age 40, the difference is the same as age 20. But in this case, if we assume the slopes to be different, now the question of which one is higher than the other becomes very complicated, because, well, perhaps it's higher at age 20, but it's not higher at age 60, right? At one age, perhaps the activation in one group is just the opposite as the other one. So what do you mean by saying that the average, that the activation is higher in one group versus the other, while controlling for age, if you assume the age to be different, the age effect, so basically the slope of these lines to be different between the 2 groups? That's kind of like what when people talk about when you have an interaction, you shouldn't be trying to interpret the main effects and those type of things. And when you have a control covariate, that's why when you care about a control covariate, you typically make that assumption of the control covariate effect to be the same across the 2 groups, because if you want to control for that effect, you have to make an assumption of that effect being the same. Otherwise, there is not going to be a way to control for that. You cannot ask the question of whether there is activation in one group higher than the other at the same age level if you assume the age covariation to be different, because at one age level it could be higher in one group and another age level it could be higher in the other group. So it doesn't make any conceptual sense to ask whether it's higher in one group versus the other, unless you specify an age level.
Yeah. If you were trying to make a prediction for, if we encounter like a prediction for the activation level in this area of the brain, or a control in patient at age 60.
Exactly. So that is a fantastic question. Can you actually tell me how to do that? And you can actually ask that question. You can say, is the activation level of one group higher than the other at age 60? Even though, when assuming that the rates of activation, the change of activation with age is different between the two groups. So how would you go about testing that? I mean, mathematically, basically, how do you enter that design in here?
You'd center both age groups at 60. So you'd
Yeah.
subtract 60 from both.
Exactly. So you center them separately, but also enter them separately as two regressors, right? So we did that same trick here before, where we center them separately, but we still enter them as one single regressor because we were assuming that the slope was the same across the two groups. If you want to assume that the slope is different between the two groups and you want to compare it at age 60, what you do is, again, center them at age 60 separately at each regressor, but then enter them as two different covariates, basically, instead of as a single covariate. And that's the way. And then you enter a contrast of 1 minus 1, 0, 0, right? Because you are looking at the difference in the average activation, kind of like the y-intercept, the activation level after controlling for age at age 60. Make sense?
So under age A, are you just dummy coding the parts of the vector that would correspond to the group B?
Sorry, again, I didn't quite hear the question.
Let's say under, you have age A in your participants file, and then you have values to put in for all of the group A subjects, but then for the group B subjects, are you just dummy coding those values?
0.
Or putting them at 0?
Right, you put them as 0 for the other group. So basically, HA has the actual age values for the group A subjects and 0 for all of the group B subjects. And HB is kind of like the opposite. It has H for the group B subjects and 0 for the HA subjects. And when you center them separately, you still keep the zeros as zeros. You don't enter them as minus 65 or anything. You just keep them as zeros. But the other ones, the ones that you are actually encoding H, you enter, instead of actually the H values, the H minus 60 values for the corresponding group. Make sense?
Yep.
Okay. So that is that. Okay, so all of these that we have talked about right now is just looking at all of them. We're looking at a single condition, right? We only care about one individual condition across all subjects. And then we look at difference between subjects, right? We talk about difference between groups, and we have between subjects covariates, but we didn't ever did anything about within subject things, right? We always had a single contrast of 1 here so we just enter a single column of Y data for this, and we just enter a 1 for all of the within subject between conditions or within subject contrast. So you can extrapolate that, everything that we did, you can also extrapolate it to, well, let me just actually, before we get to that, let me see. Right, so I don't know. Well, okay. Sorry, I started talking about the next slide, not this one. But I'm not totally sure whether I want to talk about this one. This one is about ANOVA and kind of like general ANOVAs. Let me briefly talk about that. I mean, this is still all within between subjects, right? So we talk about 2 groups and 3 groups, but we didn't talk about kind of like a ANOVA designs, like a repeated measure, like a 2x2 design or 2x3 design. Sometimes you have multiple groups, but those groups are organized in this type of ANOVA way where you have like these cells, right? And you have, for example, like controls and patients, and you have medicated versus non-medicated subjects. So you have effectively 4 groups, but those 4 groups are organized in a 2x2 manner, right? And conceptually, you have two factors that you care about. One is whether you have patients versus controls, and the other factor is the medication factor, whether they are medicated or not. And you can talk about the main effects of the groups or main effect of medication, or you can look at the interaction between those 2 things. This is all kind of like the ANOVA nomenclature for this kind of like between subject design. So how did you enter all of those kind of like ANOVA, more complex ANOVA, higher? We only look at the one-way ANOVA because we had only one factor that divided across 2 groups or 3 groups, but they were all kind of like conceptually within the same factor. But what if you have this kind of like multiple factor design where you have something like 4 groups divided into a 2x2? How do you deal with that? And in general, the kind of like the general rule is this thing in here. Basically, you in the way that you specify that is by entering one individual group, so for each individual cell of your design. So it doesn't matter how complex your design is in terms of an ANOVA design, you're still going to have a number of individual cells, right, that are organized in some manner, in some multidimensional manner. So basically, the way to encode that in our second level GLM type of analysis is by creating a dummy coded variable for every individual cell. And so basically, in this case, you have this 2x2 design, you create 4 groups, right? One for the controls, medicated, and the one for the controls, non-medicated patients, medicated patients, non-medicated, right? And each of them, you're going to treat them as an individual group. So you just dummy code them as 0 for the subjects in one group, and 1 for the subjects in one group and 0 for everybody else. And then you just have to worry about specifying the particular kind of like contrast that you care about, depending on what is it that you care about those different factors, by specifying a different contrast vector in here. So the typical things that you care about is by looking at, let's start with this perhaps, because simpler, sometimes you have these 4 groups, but you just care about the difference between medicated and non-medicated. So you're looking at, well, what is the average of the activation in these 2 groups compared to the average of the activation in these 2 other groups. So the way to actually encode that, because you have these 4 groups in the design, is by creating this 0.5 minus 0.5, 0.5 minus 0.5. Right? So this is the way that we encode it. This is the first, we enter 4 cells, and the order of these cells is basically these 1, 2, 3, and 4, right? So we have, this is cell 1, this is cell 2, this is cell 3, is cell 4, and the cells are basically 1 per column of the design matrix, right? So I created one effect here that encodes the subjects in this cell, then another one here that encodes the subjects in this cell, another one, the third one here for subjects in cell 3, and the fourth one for subjects in cell 4. So the only thing that you need to care about when you want to look at whether main effects or interactions across all of these things is kind of like how to aggregate across these 4 cells. So in this case, if you just care about the difference between these guys and these guys, you want to compare the average between these 2, and the average between these 2, you can compute it by using a 0.5 contrast across the second and fourth column, and that's why you have this, well, let's say the average of this first and third column, so that's why you have a 0.5 and 0.5 here to kind of like complete the average activation between these 2 groups, and then you want to compare that to the average activation between these 2 guys, so that's why you enter a 0.5, 0.5 here, but with opposite sign, so that you are comparing the average activation between these 2 groups, compare that to the average activation between those 2 groups, and that will be basically the main effect of medication in this 2x2 ANOVA design, right? So if you actually choose like an SPSS or whatever software and enter that same data basically into a 2x2 ANOVA design and ask the question of what is the main effect of medication, that is basically exactly the same statistics that you would get here by using this particular contrast. And if you care about the contrast of the main effect of the other factor, basically the patient versus control factor, you just do the same thing, but now you're aggregating across these 2 things, so the first and the second contrast cell, and then compare that to the average of the third and the fourth. So that's why you do like a 0.5, 0.5 across the third and the fourth, and compare that to the 0.5, 0.5 average activation between the first 2, which are these 2 guys. Does it make sense for the main effects?
Sure.
Right, and the same thing happens for the interaction. The interaction is basically asking whether the difference between these 2 is different than the difference between these 2, right? So you are asking now whether the difference within the controls in medicated versus non-medicated subjects is different itself than the difference between the patients in the medicated versus non-medicated subjects. And the way to do that is basically by looking at this interaction vector. You're looking at a -1, 1, 1, -1. Vector to compare those differences. Basically, that's kind of like conceptually you are looking at the 1, -1, 0, 0 vector, which is looking at the difference between these 2, and comparing that, and you're looking at a 1, -1, 0, 0, 1, -1 vector to look at the difference between these 2, and then you are comparing those 2. So if you have like a 1, -1, 0, 0, and then subtract a 0, 0, 1, -1, you end up with this, basically a -1, 1, 1, -1, basically. That's an interaction of the 2 factors. Basically, it's a 2-way ANOVA interaction between these 2 subject factors. And in very general, I mean, this is relatively simple when you have only 2 groups, right? Because it's relatively simple to come up with this. But when you have more than 2 groups and when you have more than 2 levels of each factor, it becomes increasingly complex. So the general rule of thumb is basically, well, this works to actually create the contrast. If you want to create these contrasts and you are not exactly sure how to create them, just specify them separately as a contrast across the first factor and across the contrast across the second factor. So for example, if I just care about the interaction between these 2, that's basically saying that I care about the difference between controls and patients. And what do I care about in terms of medicated versus non-medicated? I care about the difference between those two. So if I create a Kronecker product of this vector versus this times this vector, that gives me basically this vector. And let's say that I care about the difference between the patient medicated and non-medicated, but I look at the average effect between the controls and patients. That's basically specifying that I care about the average across these two factors, and across this factor, the average across the two levels, and in this other factor, I care about the difference between those two levels. So basically, the Kronecker product of this vector and this vector, that gives you basically this vector. And the opposite thing for this vector. This Kronecker product basically gives you this vector here.
What does KRON stand for?
Sorry again?
What is the KRON? What is
that? That's the Kronecker product. That's a MATLAB thing. Well, it's a mathematical thing. You know, the Kronecker product of two matrices doesn't sound familiar. Kronecker, Kronecker. Perhaps I'm pronouncing it weirdly. It's a mathematical type of product that is useful for in linear algebra for converting matrices to vectors and things like that, because it's basically like let me see if I can. Well, just 1 second. Let me stop sharing and share my other window for a second. This one.
That's like the.
So I can go here. Yeah. So, oops, I don't know why. Let me push this out. Okay, so Kronecker product, let's say you have a matrix that is this. And now you have a matrix that sounds, I don't know, something like that. The Kronecker product is basically the product of this element times the whole matrix, and then this element times the whole matrix, and then this element times the whole matrix, and this element times the whole matrix, and all of those kind of like put together. So if I do something like that, sorry, Kron AB is going to be like a 6x6 matrix, where this portion of it is 3x3 thing is this original thing multiply all by this value, and then these other 3x3 things in here are the original matrix multiplied by this value, and so on. So that's kind of like it's like an explicit expansion of multiplication type of operation. It's called Kronecker, and in MATLAB it's just Kron, and if you use Kron like, I don't know, for example, -1, 1, and then I use like 1, 3, it's going to create like two matrices, right? This is my 1, 3, like 3x3 ones matrix, and it creates like a -1 times that, and then a 1 times that in here. So it's like an expansion type of thing. In the case of the contrast that I was looking at, if I look at that, the Kronecker product of this looks like the vector that we care about, remember, for the interaction. And if I look at the Kronecker product of this is the main effect type of vector, right? The contrast vector. And it works also in general when you have more complex design. So let's say that you have something like this. Let's say that you have the first factor has 3 groups, and you care about the difference between the 3 groups, right? So you would enter for that factor something like this contrast. This is like the diff I across the 3 groups. And let's say you have another factor that only has 2 levels, and you care about the average across those 2 levels. So conceptually, you would have these 6 cells in your design, because you have 3 groups, and then you have 2 groups on the other one. So you have this 3x2 design. So you have 6 cells. So how do you specify that contrast vector for that difference? You will specify like this. These are the contrast matrices that you will specify for this particular contrast. It's just these are the 6 numbers that would form a contrast vector across those 6 cells. And this is a contrast matrix because you will be looking at like an F-test. So basically, okay, this Kronecker product is just like an easy way to get to creating these contrast vectors in a consistent manner when you have very complex, like ANOVA designs with multiple levels and multiple factors and multiple levels per factor and things like that.
Can you put that in? Is it possible to put that into the could one of us put it into the configuration file if we had that?
That's a good point. I think.
And maybe it'd be better if we didn't, just so we can see explicitly what it.
I think currently it doesn't, but it's simple enough to allow you to enter like a MATLAB type of command in those things. So I'll look at that, and yes, you should be able to enter that type of cron line in there as well. That's what you mean, right? Or you mean like
Yep.
okay, yeah. Okay, so let me go back to the original. This. Okay, so that's that contrast. Okay, so that's in general, when you have more than 2 levels or more than 2 factors and each one has more than 2 levels, then kind of thinking in terms of the individual cells and defining the contrast manually becomes a little bit more complex and time consuming. So using this Kronecker product type of trick allows you to generate those contrast vectors in a more consistent, less error prone type of manner. Okay. So I think I still have a little bit more to talk about but I think we're going to break it like this because I think that's probably enough for today. Should we like reschedule and continue talking about this? I still have a couple of other things to talk about for the individual when you have like for all of the within subject contrast that I never mentioned so far. But I think I'm going to leave that for the next talk, if that is okay with you guys. What do you think?
Yeah, that sounds good to me.
I just have 2 questions.
Sure, go ahead.
Just because I might try to attempt something in the next couple hours. Is it possible to put in, so let's say you have a covariate that you don't have 1 covariate for each subject, you have 2, you have 1 for each condition.
Yeah, right.
How would you specify that?
Right, you can enter as, so when you have multiple covariates and when you want to make those covariates, well, when you have multiple covariates, you can think of them independently as what you want to do with each covariate separately, right? So it's kind of like the same thing as we saw with age or motion. I mean, sometimes you want to use a single covariate that is constant across all of the groups, and sometimes you want to make it so that the slope is different. So basically you want to create group-specific versions of that covariate to allow different slopes across the different groups. So the kind of like the same thing applies for multiple covariates. You just have to think about what to do with each covariate separately. It doesn't necessarily have to do the same logic across the multiple covariates. You can have a covariate that you assume to be constant effect across all the groups, and then another covariate where you assume that covariate to have different effects across the different groups and have different slopes. So that second covariate you created encoded as a group-specific covariate, and the first one you don't, right? So,
right. So what if you have a covariate that you expect to be different across the different conditions, where you have a speaking rate covariate? You need to specify a speaking rate for the normal condition, a speaking rate for the rhythm condition, and then you have that for 2 different groups.
Okay, right. So that is tricky. I mean, and what do you care about in the? I mean, that is what question do you care about the conditions? Do you care about the difference between the conditions, or what do you care in terms of the activation?
Be the difference between the conditions, but also between the groups or the interactions there.
Right, and you have a covariate.
Eliminate the effect of speaking rate from.
Right, so what I would typically enter for that particular, I mean, when I talk about multiple conditions, the next day that I talk about that, I'll go into more detail about that. But for that particular example, what I would typically do is just enter if you care about the difference in activation between the conditions, you also enter the difference in the covariate as the covariate, basically, instead of entering the covariate separately as 2 separate covariates. You just, and that rule generally works well, but I will have to explain a little bit more about the details to kind of see more clearly when you would not want to do that. But in most general scenarios, when you care about the difference in activation across 2 conditions, you also care about controlling for the potential difference in your covariate between the 2 conditions, right? You have like a speaking rate, and the speaking rate is higher in one condition versus the other. You want to control for every individual subject whether he or she speak faster or slower for one condition versus the other, and whether that variation explains the difference in activation across subjects that you are seeing. So the way to do that is basically by entering the actual difference in your covariate between the 2 conditions as one single additional covariate across subjects.
Okay.
Make sense?
Yep. And then the second question I had was, does the effect of a covariate have to be significant before putting it into the model? Like, would you want to see whether there was an effect of, so like if you go back a few slides, would you want to see if there was an effect of age
Right.
On activation, or is a difference in age between the two groups?
So do you need to know whether there's an effective age on activation before putting it as a covariate to control across the two groups? Or does it just have to have some amount of, like, does it need to be significantly variable in order to be a valid addition to the model?
Right, that's a good question. And generally, yes, but that's mostly for practical purposes. So I mean, if in theory, at least, if you think that covariate, I mean, you think of that covariate in whether that is going to potentially affect, and you enter into the model anything that you think that potentially may affect both the activation and the difference in the effect that you care about. So if you care about the difference between the groups, then anything that is a potential thing that may be affecting activation and maybe itself be different between the groups is a potential confounder effect. So you want to control for that.
Okay.
But in practice, that becomes very costly, right? Because you don't have that many degrees of freedom. The more variables that you enter to control covariates, the less degrees of freedom that you have. You end up having like a practical scenario where if you enter too many covariates, you are going to reduce sensitivity of your analysis because you are controlling for too many things and you don't have the power to actually control for that many things. So it's a little bit of a trade-off. If you enter something that is not really significant, that was not significant to begin with, you are just reducing your degrees of freedom for no good reason because you are not adding more, you are not gaining anything. But if you fail to include something that was actually producing a potential confounding effect, then you are having a worse scenario, because in that case that will be actually giving you a confounding effect where you see something that is significant when it actually shouldn't be significant, which is worse than the first scenario. So typically you wanna fall on the side of being too conservative, but you have to keep in mind that the degrees of freedom and the sensitivity of your analysis is gonna be reduced the more covariates that you enter. So you try to be, I don't know, as thorough as you can without reducing too much your degrees of freedom. And so in many practical scenarios, you actually, one way to do that is by actually looking at whether there are any difference between the groups, because for something to be a confounding effect, it has to be different. At least when looking at the difference between the groups, for something to affect as a potential confounding effect, it has to actually be different itself between the groups. Otherwise, it wouldn't introduce a confounding measure. It would just add noise, but it wouldn't confound your difference. It wouldn't appear as an artifactual difference between the groups. So one way to go about that in practical sense is that many people just look at the confounder variables, look at whether any of them are different between the groups. If some of them are, those variables are the ones that are entered into your model as control covariates, because those are the ones that are dangerously acting as confounding effects in your model, basically. Make sense?
Yes. If you expect if they're not different between groups, but there is some variety maybe you're expecting the effect of them to be different in different groups. So so the age levels are the same across groups, but you anticipate there being a different effective age in the stuttering group versus in the control group.
Right, like different slopes, like in this example here.
Yeah, exactly.
Yeah. In that case, then you definitely need to. Well, if that is acting as a confounding effect, then you probably want to enter them as thorough as possible, like this. But I mean, that is a tricky question. If you have a good reason to think of them as being separately, having different slopes, then definitely yes. If you don't have a very good reason, then you might actually test that and look at whether they have different slopes. And if they give you that they have different slopes, then you enter them as have different covariates per group. And if they don't give you an interaction effect, then just enter a single covariate that is constant across the two groups. So, I mean, it's all a matter of in practical terms of sensitivity. If you had infinite number of subjects and then you would enter the more complex confounding effects as possible, because you are not going to lose that much by being that extra conservative. But to the degree that is never the case, then you want to try to minimize the model to as much as possible, or the complexity of the model, while being as conservative as you can reasonably be, basically.
Gotcha.
So it's a little bit of a trade-off. I don't have a definite answer for that. That's right.
I'll ask you if I run into anything or try something that seems
Right. I mean, you can start with that. I mean, you can start with, if you have a a number of potential confounding effects, you can actually look at whether those confounding effects are affecting activation and whether they are different between their groups. And then you will end up with a reduced set of potential confounding effects. Instead of having all of those things that could be affecting your data, you end up with 2 or 3 that actually could be affecting your data because you saw that they are different between the groups and they actually have an effect on activation. And then when you look at the difference that you care about, you enter those individual subset of covariates that you found to be most problematic, right?
Yeah. Maybe to just give a more concrete example. So for, let's say, motion, let's say like average motion in the scanner. If I see that there's so I added that into the model, into my second level model. And we didn't see that there was much difference between whether I included it or not.
Right, that's a great example there. I mean, motion, if you have reason to expect that your subjects move more in one case than in one group than the other, then you definitely need to enter them as. If you don't expect that to be different because there is no a priori reason to expect more motion, and you actually don't see that difference in motion when in your subjects, then you don't have any good reason. You could enter it as a post-hoc analysis where you just want to justify to your reviewer that you run your analysis, and when you control for motion, you get the same results. Then yes, you run it as an additional analysis just to make your reviewer happy, or to just like add it to your appendix as an additional analysis that you run just to make sure that there was motion that was not acting in some weird way that you didn't account for. But if you don't expect any evidence for motion to be an effect, and you don't see any evidence of motion to actually be different between the groups, then you typically don't enter it in your main model, because that would be one of those cases where you would be wasting degrees of freedom, so to speak, basically.
Right. Okay. Thanks.
No problem.
Can I ask something on a different topic, but that is relevant for Saul and Alfonso?
Sure, go ahead.
Yeah.
Alfonso, if Saul were to send you his fMRI reliability paper, do you think you would have time, like over the next few days, or I don't even know, the weekend? I don't know what you got going on the weekends, but to look at the method section, just to give that a once over